Yes, good afternoon, all of you. In the last class, we have started the special transformer connections. In that, we have total four connections: delta zigzag, star zigzag, open delta, and SCOT connection. So first, we have seen the first two: delta zigzag star and star zigzag star. Okay. Now, totally, uh, if you take the previous four main connections: delta delta, star star, delta star, and star delta. These are the main four connections, and previous two connections are delta zigzag, star zigzag. So we divided completely the six connections into two groups: phasor group 1, phasor group 2. Okay, just for simplicity we divided all the transformers into two groups, so that this point directly we will utilize about this phasor group in case of parallel operation of transformer. So that we will see today itself. Okay, phasor group. One group is the vector groups belongs to 0 degree, 180 degree, we call group 1, and the remaining 30 degrees lagging, leading, 150 and 210. So all these vector groups we combine as group 2 it is. So which connections will give these vector groups? Delta star delta, star zigzag star. Okay, so you should know about this zigzag, delta zigzag and star zigzag, which connection will give which type of vector group. For that I given one connection in delta zigzag star and star zigzag star. Okay, now let's see the next connection, open delta connection. Next one, third connection in the special transformer connections, third one, open delta connection. This is also called VV connection, open delta or VV connection. Open delta, if any one side is gets open, that will become V. Okay, don't say inverted V, anything, but we call it is as simply VV connection. Delta is becoming VV or open delta connection. So anything. Now, first of all, one important point regarding open delta is what? This connection is suitable for a three-phase transformer bank or single unit of three-phase transformer. In the differences, when we started three-phase transformer, there I given one statement: open delta possible for three-phase transformer bank. Means what? Three individual single phase transformers you can connect in delta delta, so that is converted to three phase transformer. Now in that case only open delta possible, but it is not possible for single unit of three phase transformer. Okay, so the reason also given at that time. So write one point here: it is possible, it is possible for a three phase transformer bank, a three phase transformer bank, nothing but three individual single phase transformers. If you connect as a three phase transformer, that is we call three phase transformer bank it is. Okay, now let us consider three identical single phase transformers, because when you connect three single phase transformers into a three phase transformer, there you should take identical same single phase transformers you should take, because same voltage rating should be there for three phases. For that reason, let us consider three identical single phase transformers. Okay, right, considering three identical single phase transformers, three identical single phase transformers, each having same voltage rating, same current rating. Okay, that means volt ampere of each transformer is same, so that is we are taking now. And these three identical single phase transformers, first we will connect as a delta delta transformer. Okay, first we will take delta, then we will go to open delta. There we will observe what are the changes in the capacity of open delta from delta delta connection. Observe. Connecting the three identical single phase transformers as delta delta. Primary three phases connecting as delta. Only electrical connection it is. Magnetically they are not connected. Magnetically single phase transformers separated, no. There are three single phase transformers in front of you. Only the windings, terminals we are joining like a delta. Let this is primary side, delta connector. Three single phase transformers. Let us consider A, B, C connected in delta delta. Okay, connected in primary delta, secondary also similarly delta. All secondaries joining as delta. Now let secondary side small e, B, C. Okay, so I'm considering this is A phase, terminal A phase, and this is the line B, and this is line C. Similarly here, this is terminal A, line A, and this is I'm coming in a sequence. So this is B, and this is C. Okay, first A, and then B, and then C. As it is, I taken again A, B, C. Here also same A, then B, then C. Three phases, primary, secondary. Now we have taken three identical single phase transformer. Let the rating of single phase transformer rating, I will write here. Each single phase transformer having voltage rating V, current rating I. Primary side V1 I1, let us consider. Secondary side V2 I2. Each single phase transformer, primary voltage V1, current I1, secondary voltage V2, current I2. Okay, each single phase transformer. Now what is the voltage here for each phase? This is V1, this is V1. From here to here V1 it is V1. And what is the phase current in this? I1, primary side. Similarly, secondary side, what is this voltage across each phase? V2. Anyhow, in delta, line voltage equal to phase voltage only. So therefore, directly this is V2. Okay, V2. Phase voltage, line voltage, both are same. And this is also V2. A to B, B to C, C to A. All voltages are same in three phase. That is balanced. All the line voltages are same. Similarly, primary side we give supply voltage having same magnitude with 120-degree displacement. Okay, this is primary side. Now we are operating three single phase transformers by connecting in delta delta and by giving three phase supply to primary side here. Okay, that ratings we are rating. Similarly on secondary, let this is voltage V2 across each phase and current is I2. Okay, this is the phase current. I2 and I1 are the what? Phase current of primary, phase current of secondary. But in delta connection, we know what is the line current always? Root 3 times of phase current. Similarly here, line current. What is the line current now? Root 3 times of phase current. What is the phase current? I1. So root 3 I1. Similarly, secondary side, phase current is I2. Then what is line current? Root 3 times of I2. Okay. Phase voltage V2 and phase current I2 we taken. Then what is the line current? Root 3 I2. And what is the line voltage? Same as it is the phase voltage. Phase voltage, line voltage same. Okay, this is delta delta. Now let's see first what is the kVA rating of this delta delta. Then we will check for open delta similarly. First complete up to this. Considering three identical single phase transformers right here connected in delta delta. Connected in delta delta. Write this connected in delta delta, considering three identical single phase transformers connected in delta delta. So this is the figures. Okay, now let's see what is the volt ampere rating of this delta delta. So with respect to secondary, I'm writing anywhere you can write. So I'm writing with respect to second kVA rating of delta delta. In three phase, how to write? What is the basic equation of kVA? Single phase, what is the equation? Complex power, VI, voltage current product. If it is three phase, what is the equation for volt ampere rating? 3V phase, I phase, or what is the other formula in terms of line values? Root 3 VL IL. Anyone you can use based on the availability in the given data. If phase is available, 3V phase, I phase you can take. Or if line voltages are available, directly use this equation, root 3 VL IL. Both are same. I previously also given how it is, both are same. Okay. Now kV of delta delta is root 3 times of VL IL. Now tell me here root 3 line voltage. What is the line voltage? V2 into what is the line current? Root 3 I2. Line current is root 3 I2. Therefore, what we get? Root 3 is 3 V2 I2. So what we got? 3 V phase I phase. What is V phase? V2. What is I phase? I2. So that is only we got. So if you know the volt ampere rating of three single phase transformer, what is the volt ampere rating of single phase? V2 I2 only, no? For one single phase transformer, volt ampere rating is V2 I2. If it is connected in delta, what is the volt ampere rating? 3 times of that. So directly 3 into kVA of single phase. Remember this. Okay. Directly you can write 3 times of single phase transformer. So for star star connection also same, you will get 3 times of that single phase kVA. Directly you can give the answer 3 times because 3 single phase transformers connected in delta delta. Completed this. Next we will take open delta. Open delta means same delta will become open when there are three phases A, B, C, single phase transformers. Suppose in one of the single phase transformer some fault occurred. Generally faults will take place. Let us consider like that in one of the single phase transformer out of these three, one of the single phase fault occurred. Then we will remove that single phase transformer from that. Okay, single phase transformer you can directly remove. But if it is a single unit of three phase transformer, single unit, three phase core, three phases on the three limbs, then if any one phase is fault occurred, can you remove that phase? No. How can we remove? That is a complete transformer. If you want to remove, you have to shut down the transformer first, then open the complete tank of the transformer, take the core and winding outside the oil, and then remove that phase, whatever fault takes place. That is not easy task. But if it is a bank, three individual single phase transformers, so one single phase, one single phase, one single phase. If one of the single phase is fault, just remove that electrical connection enough and take it is outside. Still you can operate. If one of the single phase transformer is fault takes place, now it is a open delta. Still you can operate with remaining two transformers as open delta. You can supply to the load, to the three phase load, you can still able to supply. That is the advantage of this delta delta here. That is a transformer bank. You can still able to supply as a open delta connection. But you should take care of that open delta connection. Otherwise, if it is becoming overload, then overload means what? High currents. Then overheated. Because of overheat, the transformers will damage. Right? Right here, below this. Yes. Right now. Right below this. let if one of the single phase transformer if one of the single phase transformer gets fault gets fault and it is removed and it is removed so we can remove easily because one single phase transformer outside easily you can just remove electrical connection enough so and it is removed then it becomes then it becomes an open delta connection an open delta connection. Now draw the figure for this. So I'm removing any one phase. Suppose C phase I will remove. Primary, this completely single phase transformer you are removing means C primary C, secondary C, both you should remove here. So let's remove that. Removing that. Only A phase, B phase are connected. B C phase is removed. Now it is a open delta connection. Secondary side load connected, three phase load. Delta connection means what is the load possible to connect? Only three phase load. Single phase load you cannot connect. And supply is there as it is three phase supply to this V1 at an angle 0. This is A, this is B, this is C. So considering the sequence, terminal A, terminal B, this is A phase, B phase. C phase we are removing because of fault occurred in that it is removed. Now AB, this is AB, so V1 at an angle 0. BC, where is BC? This is BC. V1 at an angle minus 120. CA, this is V1 at an angle minus 240. Supply voltage 120 degrees. Supply voltage always balanced 120-degree displacement. Now secondary side same. This is V2, but this is what? This is terminal A. This is terminal B. This is terminal C. But between B and C, we don't have any winding here. Between these 2 points, this is C, this is point B. Between these two, we don't have any winding. But still, between these 2 points, some voltage will be there. Some voltage is there. But how much voltage it is? That we need to calculate. Then after checking about this voltage, we can say that yes, still open delta is under balanced condition. Still we can able to supply the three phase load. Check here. This is V2 and previously we taken I2 phase current it is. But here in open delta, if you observe carefully, this is I2. Now same current will come to the load terminals also. No, is it root 3 I2? Observe previously. Previously all three lines the current is root 3 I2. Root 3 I2. Line current is root 3 times of phase current. Phase current I2 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 here. But this is root 3 times of phase current. But once it is open delta, now it won't satisfy the line current phase current relation. Then directly, what is the current passing in this B phase? I2. So same current you should take here also. Means in the line, the current is not root 3 I2. The current is same as I phase current. You should take I2 only, but not root 3 I2 because it is not satisfying. Same current will go, no? Same current. So this is I2 only. Now we need to check these voltages are balanced or not first. And most of the people will get doubt. Sir, how KCL will satisfy here? KCL, how it will satisfy? KCL means sum of incoming currents equal to sum of outgoing currents, or sum of all incoming currents equal to 0. Sum should be 0, or sum of all outgoing currents should be equal to 0. Okay, KCL. But KCL will satisfy, you should take the vector addition, not direct addition here. not directly sum. Like in DC, you can write, suppose this is a node. This is 1 ampere. This is 2 ampere. Then what should be this current? 1 ampere. Sum of incoming currents equal to sum of outgoing currents. So 1 plus 1 equal to 2. Yes, satisfied. Like that, you can apply for DC case, but for AC analysis, you should not take directly this sum 1 plus 1. So here you should take vector addition. Okay. So anyhow, we need to check mainly voltages are balanced or not first. How to check voltages? How to check it is, let the A phase voltage is V2 at an angle 0 and B phase voltage is V2 at an angle minus 120. But C phase is removed here. C phase is removed because of fault in this. But still between BC, points BC, some voltage will appear between the terminals, and how much voltage we need to calculate. So to calculate that voltage, applying KVL in this loop, applying KVL in this. Then according to KVL, what should be the sum of voltages in the loop? 0. So let's apply that. See, A to B, VAB plus this is VBC plus VCA equal to 0. This is vector addition. Okay. Sum of voltages in the KVL, by applying KVL, it should be 0. Now from this we have AB. This is A, this is B. VAB is what? V2 at an angle minus 120. VBC unknown for us. That voltage we have to calculate. And VCA also we have V2 at an angle 0. Substitute here. VAB, V2 at an angle minus 120 plus VBC unknown for us plus VCA. CA, this is A, point A, VCA. V2 at an angle 0. Then calculate VBC from here. Minus of V2 at an angle minus 120 plus V2 at an angle 0. Okay. Calculate that value, how much? Calculate VBC. Use complex calculation in your calculator. Yes. That is only the reason why we are not using three-phase transformer directly. Because in single three-phase transformer, it is not suitable. Open delta, you cannot perform. Yes, even though, however, you will get here, primary side also it will be balanced. See, this is what terminal A it is, terminal B it is, terminal C it is. Between A, B, between A, B, what is the voltage here? This is A, this is B. V1 at an angle 0. If you calculate same as it is secondary side, this voltage also will get balanced. Whatever you got here, V1 at an angle minus 20, same will appear. Same will appear. Still the voltages are balanced. That is the advantage of this open delta. Even if one phase is removed. Now many people will ask doubt. Then what is the use of that delta? I will use continuously open delta only, because one phase is removed, cost is reduced. One phase is removed, no, cost will reduce. But this is a temporary purpose, not permanent purpose. Whenever any one phase is fault, for short time without disconnecting the load completely, you can give some load still from open delta. This is a temporary purpose, not a permanent purpose. Okay, there is a problem in this. I will tell how much that is. No, V2 at an angle, VBC, how much you got? VBC equal to how much? I1 at an angle 120. Okay, see, VBC equal to V2 at an angle 120. All of you getting right? Now, can we write this V2 at an angle 120 means V2 at an angle minus 240? Okay. Can we write like this or not? Yes, you can write. V2 at an angle 120 is nothing but V2 at an angle minus 240. See, let this is V2 at an angle 0. This is V2 at an angle minus 120, lagging with respect to that. Now this is V2 at an angle minus 240. So if you take from reference of this one, first one, this is 240 degrees minus, lagging, no, it is 240. But if you take directly in this direction anti-clockwise, how much angle it is? 120. But what 120? Plus or minus? Plus. Leading means plus 120. So you got 120 plus 120, that is same as minus 240, both are same. Now observe all the voltages one time. VAB, VBC, VCA, still having same magnitude of voltage V2 and balanced by 120 degrees. So voltages are balanced or not? Yes. VAB, V2 at an angle 0. Now VBC, we got V2 at an angle minus 240. And VAC, this is VAC. This is VAC, this is V2 at an angle minus 120. Okay. VAC or VCA. What is VCA? V2 at an angle 0, no? V2 at an angle 0. And what is VAB we taken? VAB we taken V2 at an angle minus 120. V2 at an angle minus 120. Between A and B, what is the voltage? V2 at an angle minus 120. Between B and C, what is the voltage? V2 at an angle minus 240. Between A and C, what is the voltage? V2 at an angle 0. So still the voltages are same magnitude, V2, V2, V2. Observe, all having same magnitude, and 120 degree displacement each other. Now this is a three-phase balanced voltages or not? Yes. So this VBC, we got V2 at an angle minus 240. So same I written here. So even if you remove one of the phase, still the voltages are balanced only. So you can supply three-phase load still. But how much you can supply? Can you supply like previous delta capacity? No. For that, we need to find what is the capacity of open delta first. Before that, write one point here. Write one point. Therefore, if one of the phase gets fault, if one of the phase gets fault, if one of the phase gets fault, still it is possible to supply a three-phase load. Still it is possible to supply a three-phase load because the voltages are balanced. The voltages are balanced. Now, what is the kVA rating of open delta? What is kVA of delta? 3 V2 I2 we got, or 3 times of kVA single phase we taken. Similarly, kVA of open delta. Let's find this. kVA of open delta, VV connection. What is the formula in three phase? It is supplying still three phase load. So actually it is root 3 VLIL formula. Now if you write here root 3, what is the line voltage now? Observe, line voltage same V2 only. Whatever is there in delta, now also same V2 only. No change in the voltages. So voltage remains same V2. But what is the line current now? Is it root 3 I2? No, I2 only flowing, because same current directly will come outside. Okay, same I2 we have to take, not root 3 I2. So current is now only I2, not root 3 I2. Only in delta root 3 I2, but in open delta it is directly I2. Therefore, what is this? Root 3 V2 I2. Nothing but root 3 V2 I2 is the volt ampere rating of single phase transformer. kVA single phase. Right. Therefore, the open delta kVA is root 3 times of single phase kVA. And what is the kVA of delta delta we got? This is 3 times of kVA single phase. 3 times. So delta delta capacity is 3 times of kVA single phase, but open delta capacity is only root 3 times of kVA single phase. So capacity of open delta will reduce. Capacity of open delta will reduce because one of the phase gets fault. How much reduces? This question is important. What is this value? 1.732 into kVA single phase. But how much you got previously for delta delta? 3 times of kVA single phase. 3 times. Okay, write that relation. Right. Therefore, right here, therefore, kVA open delta divided by kVA delta delta. What is the open delta kVA? Root 3 times of kVA rating of single phase transformer divided by kVA delta delta. How much we got? 3 times of kVA single phase transformer. Now kVA single phase same, cancel it is. Then root 3 by 3, nothing but 1 by root 3. Then 1 by root 3 value is what? 0.577. Therefore, the kVA rating of open delta is only 57.7 percentage of kVA rating of delta delta. The most repeated question many times in many examination is directly this equation only. How much open delta can supply when compared to delta delta? How much it can supply? Only 57.7% of that capacity it can able to supply. Okay, and how much it is underloaded now compared to delta delta? Supplying 57.7%. How much it is not able to supply? Remaining 42.3%. It is not able to supply. The capacity of open delta is only 57.7% of delta delta capacity. Okay, don't confuse in the two percentages. Sometimes they will ask what is the capacity of open delta or how much less it is supplying compared to delta delta. Now make a note, make a note. Remember these points. Note. Observe first. What is the open delta kVA rating? Root 3 V2 I2, or same we are writing as root 3 times of kVA rating of single phase transformer. Okay, now how many single phase transformers are working? Two are there. Total three single phase transformers A, B, C. One transformer fault. We are removing that. And still how many are there? Two are there. Then what is each rating? V2 I2. So with respect to secondary, we are talking what is the volt ampere rating of each single phase? V2 I2. So available is total how much volt ampere? There are two transformers, two single phase transformers still working are available for us. Then what is the total rating of these two transformers? One transformer V2 I2, other transformer also V2 I2. This much. This is the available kVA rating. But how much kVA rating we got? What is the total? This 2 V2 I2. But how much we got? root 3 times of or root 3 V2 I2 we got in open delta. Therefore, so first observation here is in open delta, kVA supplied by each single phase transformer is how much? So write that point below this. In open delta, kVA supplied by each single phase transformer. kVA supplied by each single phase transformer. How much? Half of that only, no? Half of this root 3 V2 I2 is root 3 V2 I2. This is the open delta. Total two single phase transformers are there in this working divided by 2. Both equally supplies. Now, what is the rating? What is this value? Root 3 by 2 means 0.866 V2 I2. 0.866 V2 I2. This is the kVA supplied by each single phase transformer under open delta condition. Okay. But what is the kVA rating of each single phase transformer individually? If you find V2 I2, this much. Now each single phase transformer actual volt ampere rating V2 I2, its capacity, but how much each single phase transformer is supplying here? Only 0.866 V2 I2 means 86.6 percentage. 86.6% only it is supplying. Now how much single phase transformer is underloaded? So little, particularly in open delta, all these percentages little confused. Okay, you should remember properly all these percentage. Open delta kVA is root 3 V2 I2. In that there are two single phase transformers. How much each one is supplying? By 2. So this is the kVA supplied by each single phase transformer. How much it is supplying? 0.866 V2 I2. Actually kVA single phase rating how much? This much V2 I2. Each single phase capacity this much V2 I2, but it is supplying only 86.6% of its capacity. Then how much it is underloaded? 13.4 percentage. So write that point. Therefore, each single phase transformer is underloaded by how much percentage? 13.4 percentage. This much underloaded because 86.6% it is supplying. How much remaining out of 100%? Remaining 13.4%. So 13.4% each single phase transformer is underloaded. Okay, don't confuse in this percentage. Yes, good. So if you see numerical, you will understand how they are asking questions. This is the first point in the note. First it is. Let's see the second important point. Second one, little more you need to concentrate, little more observe. Completed this. Underloaded means single phase transformer capacity 100 volt ampere. Okay, single phase transformer capacity 100 volt ampere, but in open delta how much it is supplying? 0.866 into 100 means 86.6 volt ampere it is supplying. How much still it is able to supply? 13.4 volt ampere it is still able to supply or not? Yes, that is called underloading. This is underloading because it is not loaded. Still it can be loaded 13.4, but it is supplying only 86.6%. Okay. Why it is supplying less? Because of the equation we got, kVA of open delta is only root 3 V2 I2 now. Then what we can do for that? It can able to supply only root 3 V2 I2. That is we got from the figure. Okay. Now I will, the second important point is there, you try to understand that. Yes, underloaded means simply it is not supplying. Good. It should supply, see, each single phase transformer is V2 I2. Total two single phase transformers available. Then what is the total it can supply? 2 V2 I2 it can supply. But what is the capacity from the calculation we got? Only root 3 V2 I2 we got. That's why it is supplying 86.6% of each single phase transformer. Not completely. Now observe second point. Second point. Now this point is concentrate little. Observe here. Suppose there is a delta delta transformer initially. Initially the three single phase transformers connected as delta delta. Okay. Then what is the rating of that delta delta we got? 3 V2 I2. Okay. 3 V2 I2 we got. Or 3 times of kVA single phase it is. 3 times of kVA rating of single phase transformer. Now let us consider this is the capacity of transformer. Now a load is connected to this delta delta. How much load is connected? The load capacity also 3 V2 I2. Try to understand this. Try to understand this one. Important. Load also connected 3 V2 I2 means this transformer is supplying full load or not? Tell me this point is clear to all of you. The delta delta capacity 3 V2 I2, or example you can take 300 kVA. 300 kVA. Now load capacity also 300 kVA. That means that this transformer is supplying full load or not? Yes. Transformer supplying full load. Whatever the rating of transformer is there, that much load you connected. That is called full load on transformer. Okay, clear all of you this point? Now load is there on this transformer. Suddenly one of the phase gets open. Now it becomes open delta. Whenever it is supplying load, while supplying itself load, one of the phase is fault. Now immediately it will become open delta. Then what is the actual capacity of open delta it can supply? Root 3 V2 I2. It can supply only this much, but load is how much connected at that time? What is the load connected at this time? Same load is there or not? Yes, load is there, same. How much load? 3 V2 I2. This much load is there. Load is 300 kVA as it is there, but suddenly delta delta becomes open delta. Now this open delta should supply whatever load is connected or not. Now already this point I said in previous classes. Transformer doesn't know anything how much to supply to the load. Whatever load required, load will take from transformer. That's it. Suppose there is a fan, ceiling fan is there. That fan requires 1 ampere to work. Now when you connect that ceiling fan to the transformer as a load, now fan will take 1 ampere only. Now is the transformer, suppose transformer wants to supply 2 amps, it can supply. Transformer cannot supply 2 amps. Whatever that load is required, load only will take. So in the same way, the load previously 300 kVA. Now also same load is there, because load is the load know that in transformer one phase is damaged, I have to load has to reduce. Load also doesn't know anything. If you connect, load will draw. Then who will take care of this? The users, or we should take care. Whenever any one of the phase is fault, as it is becoming open delta, and the capacity of open delta is only this much, root 3 V2 I2. But if you connect a load which is the capacity of delta delta 300 kVA, then definitely this open delta will become overload or not? Yes. How? In order to get 3 V2 I2 in this equation, what you should make changes? Observe, check. Actual open delta is root 3 V2 I2, but we need 3 V2 I2. We need 3 V2 I2. Then out of voltage and current, which one should increase? Voltage will increase or current will increase? Load variation is current only. So this I2 will become root 3 I2. Current will become very high. So that what is this value now? 3 V2 I2. So kV of open delta becomes 3V2 I2. Why kV of open delta become 3V2 I2? Because the load connected is 3V2 I2. Now this 3V2 I2 is similar to delta delta capacity. But if you observe this equation carefully, in this equation, root 3 voltage remains same, but current is root 3 times of its rated current or not? Yes. What is the rated current of each transformer? I2. But now what is the current in each phase is flowing? Root 3 I2 is flowing. Now each phase is overloaded. How much overloaded? I2 is the rated current or full load current. Now current is becoming root 3 I2, so that it will meet that load demand. It will meet the load demand. Now root 3 I2 means what? 1.732 I2. That means 73.2% overloaded or not? Yes, it is overloaded by 73.2%. So little concentrate this point. If you understand this, some of the questions directly you can answer. They will give a delta delta transformer supplying 300 kVA load. A delta delta a three phase 300 kVA delta delta transformer supplying full load. Full load means 300 only. 300 kVA it is supplying. Suddenly in delta delta, one phase gets fault and it is removed. Then it will become open delta. Then in open delta, each single phase transformer is overloaded by dash percentage. How much each single phase transformer is overloaded? 73.2 percentage. Each single phase transformer is overloaded, because in order to meet the same load kVA, current increased by root 3 times of the previous. Root 3 times of the previous, it will increase. Then it will become 3V2I2, which is equal to load kVA. All of you clear this point? Any doubt in this still? Any doubt? So I will give that statement. Yes, each single phase transformer overloaded by 73.2 percentage. Definitely transformer will damage. That's why I said that whenever if any phase gets fault or if it is becoming open delta, we should take care. Then immediately what you have to do? Reduce the load whatever connected. How much value you have to reduce? Remove 42.3% of the load, because what is the capacity of open delta? Only root 3 times or 57.7% of delta delta. If previously 300 kVA is there, now calculate what is the 42.3% of this. Remove that much load immediately, so that your transformers are safe operation. Okay. Yes, good. We have to reduce that root 3 times. How we know fault takes place or not? Yes, one of you asking, Bhaskar. How we will know fault takes place? Suppose all these are all monitoring. If you are in a substation, what is the job of that people in substation? All this monitoring. They have meters, current meter, that is load, how much current is there, and voltage, frequency, all they will observe, not there. If they are sleeping, suppose they are not observing, then definitely transformers will damage. Their job is they should take care of that every control or monitoring. They will observe that meters. Suppose suddenly current rating increases very high, then immediately they will remove some load on the transformer by disconnecting isolators or by opening isolators. They will remove some load, then again current reduces. Like that we have to monitor. Then how we know otherwise fault is taking place or not? Okay. Yes, fluctuations happens, that is due to unbalanced load conditions or some fault conditions. suppose in, so after not nearby to your home, so nearly substation point of view, there somewhere some fault takes place, or out of the three lines, in one line complete fault is there, then they will supply the load from two phases, then there is a chances of that fluctuations. Voltage rating will not increase. Why voltage rating will not increase? Voltage rating depends on number of turns, and that is always fixed, no, in that. Load variation means current variation. Many times I said this. During summer only mostly power cuts. The reason is fault. Fault means because of this unbalancing conditions, many times happens in different phases, three phases. So fuses will burn or fuses will damage. So to replace that, power cuts will be there for some small time. Yes, you can change the third transformer. Single phase transformer fault takes place. Now you would remove that. Now, if you have readily the single phase transformer, you just replace that within short time. Now, still it is delta delta operation only. Okay. Monitoring, we have different methods. In open delta, we are taking I2 as the line current only. The line current itself I2. Both are same here because it won't satisfy now line and phase different. Both are same. Each transformer is running at, yes, 173.2 percentage. Actually, each single phase transformer can supply 100 ampere. But how much now it is overloaded? 73.2%, means it is supplying 173.2 amperes. Okay. Yes. Now from delta delta or open delta, you can supply only three phase load, not single phase, because neutral is not available here. So you cannot supply single phase. Yes, open delta you should operate for small duration, not long durations. Otherwise, you should operate for long time, means the load should be within the range, that 57.7% of delta delta. Okay, enough. Now write the point here. Write this point clearly. If a delta delta transformer supplying full load, if a delta delta transformer is supplying full load, supplying its full load, comma, suddenly as one of the phase, gets fault, comma, it becomes open delta. It becomes open delta. And the load on open delta, the load on open delta is same as delta delta, hence in open delta, each single phase transformer in open delta, each single phase transformer is overloaded by how much now? Root 3 times, or 1.732 times, or simply 73.2% overloaded it is. In open delta, each single phase transformer is overloaded by root 3 times of its rated current, or overloaded by 73.2% of its rated current. of its rated current. Now, due to this, as it is overloaded by 73%, means very high percentage, then definitely what is copper loss produces now? Very high in each transformer. If loss increases, heat increase. And if this heat crosses the limit, whatever we specified, then definitely windings will damage. Okay, comma, right, full stop. Due to this, the single phase transformers are overheated. The single phase transformers are overheated and damage. So what we should take remedy here? We should take care of this. What is that? Hence, whenever the delta becomes open delta becomes open delta, then remove remove some fraction of load, remove some fraction of load, such that how much we have to remove? Suppose if it is full load, how much we have to remove? 42.3% we have to remove, because how much it can supply? 57.7% of delta it can supply, such that an open delta can supply only 57.7% of delta capacity without overloading. So open delta can supply only 57.7% of delta capacity. That is without overloading, because root 3 V2 I2 only there. But now how much current increases? Root 3 increases, root 3 times of that I2. That's why it will damage. So remember this point. If you know this theory, some questions directly you can answer. So I will show you one question in the previous ESC examination, how much important the theory required in this open delta first. Okay, completed all of this. Now write one more point before that question, then we will see that. Right, next point, third. This is regarding utilization factor of open delta. Utilization factor, UF. Utilization factor. So what is utilization factor? Means how much you utilized from the available. Simple. What is utilization factor? How much you are utilizing from the available. That may be anything. That may be currents or voltage or capacity, anything. So we are comparing here capacities. So it is defined as it is the ratio of KVA rating of open delta KVA rating of open delta to the available KVA rating. So what it means? How many single phase transformers available? Two transformers. Each transformer rating how much? V2 I2. Like the total 2 V2 I2. But how much you got KVA rating of open delta? Root 3 V2 I2 only we got. Now how much percentage utilized? Check here. So utilization factor of open delta is KVA open delta. How much? Root 3 V2 I2 divided by what is the available KVA rating? Two single phase transformers available, each one V2 I2, other transformer V2 I2. Okay, now if you calculate root 3 V2 I2 divided by 2 V2 I2, V2 I2 gets cancelled, root 3 by 2, the value of root 3 by 2 is 0.866. That is, the utilization factor of open delta is 86.6%. How much it is not utilizing? 13.4% is unused. 13.4% unused. That is drawback for us. We are not getting 100% of open delta utilization. We are getting only 86.6% from the total available kVA. We are not getting this. 13.4% is unused or waste it is. Okay. Remember this utilization factor of open delta. How to remove fraction of load? See, how to remove, suppose take your home is the load on open delta. Previously you are getting to your home, there are so many loads, motors, or refrigerators or air conditioners, so many are there, for example. So you are getting directly from a delta delta transformer. You are connecting full load. Suddenly in the transformer one phase fault. Now immediately it will become open delta. Now how to remove that fraction of load means what? Now just switch off some of the loads in your home. That's it. Some load you are removing. How much you have to remove? That you have to calculate. If you switch on this many devices, the load will reduce to this much by calculation. Approximately calculate and then switch off that load. Then 42.3% if you remove, it can able to supply safely. Open delta will supply that remaining like that. Okay. Practically, where we use this, practically delta delta using is very less application. Okay, practically we are not using delta delta. Why? Delta delta suitable for three phase loads only. It is not at all suitable for single phase. So domestic purpose we never use delta delta. Only for some applications wherever you need only line voltages, that is only three phase voltages, there you can use delta delta. Okay. So we don't have any particular application. So when we use delta delta, you should take care for any load that is. Now, what is 86.6% means? From the available capacity, how much this connection is giving output. So available two single phase transformers, each rating V2I2, total 2 V2I2. So from the open delta, how much capacity you got? Root 3 V2I2. Okay. Next, see the question. Question on this. Try to read this carefully. Consider the following statements regarding three-phase transformers in open delta connection. Read the statements. Yes, it is there, but we are not using. That's it. Unused means not heat. Suppose a single phase transformer can supply 100 volt ampere, but in the open delta, how much it is supplying each transformer? 86.6 volt ampere supplying, and 13.4 it is still able to supply, but we are not getting from open delta. That's it. Unused it is. What is the answer for this? Tell me. See, open delta being a temporary remedy when one transformer forms delta delta system is damaged. It means one of the single phase transformer is damaged in delta delta and removed from service. So this is a temporary purpose or permanent purpose? Open delta is a temporary purpose. So this is right. Okay. Next, the volt ampere supplied by each transformer is half the total volt ampere and the system is not overloaded. So tell me, in open delta, how much each transformer is supplying? 86.6% of its capacity, not half. Each single phase transformer is supplying 86.6%. So, but they given half here, so it is wrong. Okay. Next, an important precaution is that load shall be reduced by root 3 times. Yes, we have to reduce the load. How much load we have to reduce? How much load we have to reduce? It is, if you take same load, root 3 times overloaded. So you have to reduce by root 3 times. Then it will come to open delta capacity. So this is also correct. So 1 and 3, option B is right. So I said many times, particularly for engineering services, questions are very easy. The only thing is you should have full of subject. You should be full of subject. If you know each and every concept well, then only you can answer that questions. Now, this is in ESC, we are getting these models, but right now in GATE examination from this year, GATE 2020, it is introduced MSQ questions, multiple select questions. Means in that question, like one option may be right, or two may be right, or three may be right, or four also may be right. So you should answer whatever the number of options correct. This model only they are. The MSQ questions are this model only. Actually, we are getting in engineering services this model, but they given with a special name like in GATE again, multiple select questions. Next, one more question. Serious question. When one transformer is removed from a delta bank, read the question. In 2020, we don't get MSQ, but maybe next year we can expect again. See, in the second statement, so just now I given previously in the note, what is the kVA of open delta? Root 3 V2 I2 we got. So in that, what is the each single phase transformer supplying how much? Root 3 V2 I2 by 2. This much it is supplying. Then what is this value? 0.866 V2 I2. So actual V2 I2 is the capacity of each single phase transformer, but how much it is supplying? 86.6% it is supplying in open delta case. Now given in the second statement, the VA supplied by each transformer is half of the total VA. Total VA is this much, open delta. But how much each transformer is supplying? 86.6%, not half. That's why it is wrong. Clear? See the question. When one transformer is removed from a delta bank of 30 kVA transformer. So delta capacity 30 kVA. The capacity of resulting three-phase transformer in open delta. So we have the relation directly. So direct questions you will get from this relation only. What is the kVA of open delta? 0.577 times of kVA of delta. 57.7 percentage. So this is 0.577 into delta capacity 30. Then calculate. This is 3515 means nearly 17.3 kV. This is the capacity of open delta. Okay. Yes, in MSQ, suppose if three options are right, but you mark only two, then your answer is wrong only. For that, you need to take care regarding MSQs. Okay. See, here the meaning of this is what the volt ampere supplied by each transformer is half of the total volt ampere. Actual, if you take initial delta, what is the total volt ampere? 3 V2 I2. 3 V2 I2, and half of that is how much? 1.5 V2 I2. Okay, but how much it is supplying here in open delta connection? Each single phase transformer is supplying only 86.6%, not half it is. Next, don't confuse. Remember the node points. Remember the node points. Yes, for competitive examinations, level of questions almost ESC, because questions in gate examination little difficult, but engineering services questions a little easier compared to that. But conceptual. Without concept, you cannot answer questions in ESC. But in gate examination, they will give questions little tough, but not that much depth. But ESC will have more depth. Okay. Let's see next one. Scott connection. Fourth connection in the special transformer is Scott connection. So this regarding Scott connection, now I'm not giving the complete information, which is not at all required for prelims examination. Only for engineering services it is required. For gate, you no need to study Scott connection. Okay, we don't have in syllabus. Only for engineering services. For prelims point of view, I will give whatever the required information right now. And once you come to mains, so there we will see about complete phasor analysis of this Scott connection. And for competitive examinations, it is important. Scott connection also there in competitive examinations. First, Scott connection. The main purpose of this Scott connection is to convert the available three-phase supply. The available three-phase supply into two-phase supply. Available three-phase supply into two-phase supply. Or if you have two-phase supply with you, you can convert two-phase into three-phase. Anything it is. You can convert a three-phase voltages into two-phase voltages, or two-phase voltages into three-phase voltages. That's why this connection we also called, it is a phase conversion transformer. Phase conversion transformer. Phase conversion it is. Either two-phase to three-phase or three-phase to two-phase. So we call simply a phase conversion transformer. And it is invented by the scientist named Charles F. Scott. Charles F. Scott. That's why we call it is Scott connection simply, and also called phase conversion transformer. Now, what is the main thing to convert available three-phase into two-phase? Why we should convert? Yes, for some of the applications, like welding applications, we have arc welding applications. In arc welding applications, we need a two-phase supply. Generally, in welding transformers, tell me, this is also important question. Welding transformers we have separately. Same, everything is same principle, operation, everything is same. But in welding transformers, which one is high? Voltage is high or current is high? Tell. For welding transformer, which rating required? High rating. Voltage is high required or current is high required? Tell me this. Yes, enough. Current required high value. Why? During welding, we need to melt. That is, welding means what? Melting the materials only, no? Then joining. Different types of welding, so that you will see clearly about welding in utilization of electrical energy. In your engineering, one of the subject for us. Okay, there you will see about clearly welding. So for that welding applications, two-phase supply we use. Two-phase supply. Two-phase supply means, what is the angle between voltages? Two voltages. The angle between voltages or currents is 90 degrees. But in three-phase system, what is the angle between voltages or currents? Three-phase voltages, 120 degree displacement. Okay, so we have one formula. For M phase system, what is the angle between voltages and currents? This is 2 pi by M, and this equation is valid for M greater than or equal to 3. For M greater than or equal to 3 it is. But for M equal to 2, it is always 90 degrees. Remember, 90 degrees. For M equal to 3, 2 pi by 3, 360 by 3, nothing but 120. Like that you can use for any number of phases, 5 phase, 6 phase, 7 phase, and so on. Okay. So available always, which one is readily available for us? 3-phase supply available or single phase available. But 2-phase readily not available. For that 2-phase, if you want 2-phase, then we will utilize this Scott connection. So this connection will convert a 3-phase supply into 2-phase supply. So in 2-phase supply, you should require the voltages and currents must be displaced by 90 degrees each other. Voltages 90. Suppose V2 of one transformer, V2 of other transformer, 90-degree displacement. Currents also 90-degree displacement. That is called balanced 2-phase supply. What is the balanced 3-phase supply? The voltages and currents must have 120-degree displacement with equal magnitude. Similarly, in 2-phase, the voltages and currents must be displaced by 90 degrees with equal magnitude. So how we will get that, I will show you in the diagram. Okay. So this is one application. This Scott connection we use for arc welding applications, and for other purposes, for low voltage rural supplies, low voltage in the rural areas, we use 2-phase supply. 2-phase supply is enough. Means when you rural means there is no much load, you no need to transfer 3 phases, only 2 phases enough, or single phase also enough if there is very less load, or if little more load, 2 phases required, then you can use the same Scott connection. You can supply that voltages to loads with only 2 phases. Number of conductors reduces, cost reduces. That is one application. And one more application is single phase induction motor. This is many times in engineering services interview question. This one. But generally, most of the students will not tell this application. They will tell only welding application, like that. They don't tell this because we have to give that information first. Otherwise, how they can tell? Remember, maybe as most of you, it is not completed induction motor. If completed in your engineering, you should be able to understand. Single phase induction motor. What is example? In your home, your ceiling fan. Okay, your ceiling fan example, single phase induction motor. Now tell me, single phase induction motor is self start or not? Single phase induction motor is a self start motor or not? No. Yes, good. Good. It is not self start first. 3-phase induction motor, self start due to rotating magnetic field. But single phase induction motor is not a self start motor. But how it is now, once you switch on in your home, now it is self start or not? Yes, self start. Because in this motor, we have arranged some starting method. In single phase induction motor, we have 2 windings. What are that windings? We call main winding and auxiliary winding. 2 windings we have. And these 2 windings we connect in parallel. Okay. Now, for the 2 windings, we give single phase supply only, but internally, the angle displacement will be there between these 2 windings is 90-degree displacement. If you remember this point in your induction motor, you can understand 90-degree displacement. For that, what we are using now in the ceiling fans, capacitor we are using. Capacitor split phase technique we call capacitor split phase. So using that capacitor, we are bringing that 90-degree displacement between the currents of main winding and auxiliary winding. That's why the single phase induction motor now becomes self start. but actually single phase we have single winding induction motor, only one winding, single winding induction motor. This motor is not self start, but two winding induction motor is self start. Now whatever we have, all are two windings only, that's why they are self start. But single phase single winding induction motor is not self start. Now here the question is, suppose there is a single phase two winding induction motor. Listen carefully. There is a two winding induction motor, main winding, auxiliary winding. Suppose there is no capacitor in that. There is no capacitor in that. Can we made this motor still self start? Yes. How it is now you can give supply from Scott connected transformer, because in the secondary side, what is the voltages we are getting? 90-degree displacement. Directly you are getting in Scott connection. Give this supply directly to single phase induction motor. Then your induction motor directly self start. You no need to use any capacitor and here. Okay, this is one method to start single phase induction motor without using capacitor, directly from Scott connection. Remember this point. But in the interview, you should also mention that is it preferred to give supply from Scott connected transformer? Is it preferred? This is one method to start. But main problem here is ceiling fan and transformer, Scott connected transformer. Ceiling fan cost is how much? Just 1000, approximately 1000 or 1200, like that. Less than that also available. Now in order to give supply to that ceiling fan or induction motor, can you buy a Scott connected transformer? Can we buy? What is the cost of the transformer? Yes, more than 1 lakh, maybe 2 lakh, depends on capacity. For 1000, can you spend 1 lakh? Never. This is not economical, no. That's why what we are using practically now, capacitor technique we are using. What is the cost of that capacitor? Just 60-70 rupees also, you will get a small capacitor. Easily with that motor is self-start. Then why we need to use all this? But that is method. We can start induction motor like that also. Okay, just remember. So those who are not aware of this 90-degree displacement in single phase induction motor, after completion of induction motor, try to read this point again one more time so that you will understand. A single phase induction motor can also be started without capacitor by giving supply directly from Scott connection. Write that statement. A single phase induction motor can be started without capacitor by giving supply directly from Scott connection. Okay. All that about single phase single winding you will see clearly in the induction motor, not now. So these are some applications of Scott connection. Mainly for arc welding we are using this Scott connection. Okay, so what is our main aim in this Scott connection? To convert available three phase into two phase. Main purpose is that. Right, next. So this Scott connection requires, in this Scott connection we have two transformers. One is called main transformer. We have two transformers in this. Two identical transformers required. This connection required two identical transformers. Two same transformers we have to take here. Transformers. And one is called main transformer and other is called teaser transformer. Other transformer is called teaser transformer. Okay. One is main transformer, other is teaser transformer. Now in main transformer, we have the tapping percentage. We will tap the winding in the connection. I will show you that. In main transformer, we will use 50% tapping. Tapping in main transformer is 50%, and teaser transformer tapping is 86.6% tapping. So what are all these? I will show you in the winding, just right. Teaser transformer is having a tapping percentage of 86.6%. Okay, next. So mainly in this connection, what we are doing, the available three phase is converting to two phase. Means how can you say it is converted from three phase to two phase? In three phase system, the angle between voltages and currents is 120 degrees. That 120-degree displacement you should convert to 90-degree displacement. If you are able to convert that 120 to 90-degree displacement, that means that you got a two-phase supply. I will show you that how it is 90 and all in the diagram. I will show you. Okay, write the connection diagram for this. Two transformers we need to take, and we will connect the two transformers electrically, not magnetically. Two single phase transformers electrically we join. Okay, see how it is. I think most of you has did this test in your lab also. This is a lab test. First, take the figure. Connection diagram. Take the figure first. So we have two transformers. One is main transformer, one is teaser transformer. Take the diagrams. So this is our main transformer primary. This is primary of main transformer, and it is secondary of main transformer. Okay. Now primary of teaser transformer, and that primary winding of teaser transformer we will tap at the 50% of primary of main transformer. Okay, here tapping is there. So we will tap the primary of teaser transformer at 50% of primary of main transformer. This is tapping point. Okay, this is the primary, and this is secondary of teaser transformer. This is secondary side. Okay, two transformers, two single phase transformers taken. Primaries are electrically connected like this. Secondaries we are not connecting. Secondaries are separate only. But primary windings only we need to join like this. Now, let us consider both having turns ratio N1 is to N2. Total some 100 turns here and some 50 turns here. Or let both same turns 100 is to 100. And this is also N1 is to N2. Primary secondary windings we have drawn. Now primary side, what we need to convert mainly a three-phase supply we need to convert into two-phase supply. For that primary side, you need to give three-phase supply. We need to give three-phase supply. For that, how much tapping we need to use in teaser transformer is 86.6%. See, this is total N1 turns. Primary is N1, total N1. But in that, how much we need to tap in the teaser transformer is 86.6%. Suppose total 100 turns, tap at 86.6% approximately. Okay, approximately some 86 or 87. So there, let us tap that. So why 86.6% required? I will give that proof also. This proof itself in ESC 20 last year. This proof itself ESC 20 last year conventional question given for 12 marks. 12 marks question. Okay. For that question, you need to draw this figure. Now, whatever the proof I will give, how it is 86.6% tapping, that is you have to show. That's it. Once you show that, you will get full marks, 12 marks for that. Okay. Remember, while writing conventional examinations, those whoever will write in future for junior engineers conventional examination or engineering services or any your state competitive examination, public service commissions, anywhere, when you are writing conventional or descriptive type of examination, remember, don't write or don't build stories there. Don't build stories. Whatever the question, if it is for 20 marks also, if it is for 20 marks also, write in one page or 2 pages maximum with clear concept in that. You will get 20 marks. Don't think that like engineering, if you fill more number of papers, more percentage of marks we get. This is completely opposite here. That will work only in the engineering. Writing more papers, more marks. Okay, but there is no use of that. So leave that. Here only concept is required while writing this conventional examination, particularly engineering services, because the people whoever will correct that papers, conventional papers, they don't have that much patience to read line by line whatever we write, line by line. They will observe your figures, and then if any equations is there or if any phasor diagrams are there, only these three they will observe. If these three are perfect in the solution, whatever you given, you will get full marks. But don't write any theory more. So write the theory, just statements, important statements, some points, but not so much lines. Theory should be as much as possible less. So primary side, we are giving three-phase supply. So I'm taking, this is point A, point B, C. Three phases, A, B, C. Primary side, we are giving three-phase source. Let this is VAB, VBC, and VCA. VCA. Now we need to apply a three-phase voltage here. What is our three-phase voltage always? Balanced or not? So whatever we have three-phase source, that is always balanced. Source means what? Generator, alternator. What is we are generating in alternators always? In alternators, we always generate the balanced three-phase voltages. So whatever source is there, always we take balanced only. Remember this point. Remember this. So I am considering BC is my reference. So I will consider this is V1 at an angle 0. So anywhere you can take reference 0 degree. So I will take BC is 0. Why? This is main transformer. See, this is main transformer, primary, secondary, and these two are teaser transformer, primary, secondary. This is teaser transformer. Don't ask why it is teaser, why it is main. So whatever scientist given, we have to follow. No, people will ask these doubts. So why we call teaser it is? Why not teaser it is? So you invent any one method and put it in the textbooks. Then I also follow same thing. This is whatever your name. Okay, don't ask this. So why teaser here he placed is, in this transformer he did not use the complete winding here. Some percentage of winding only he used, and that particular transformer he named as teaser transformer. And other transformer is main transformer, because in this transformer he utilized complete winding. See, total winding he used here, but here this winding there is no current. In this winding current will not flow here because it is open. Current will go only like this. Now why it is 86.6%? That proof I will show you. Observe carefully. So I'm taking V1 at an angle 0. This is the midpoint. Center tapping it is 50%. Then if it is V1 at an angle 0, tell how much voltage will appear here. See, for BC, nothing but primary of main transformer. BC is the primary of main transformer. If total voltage applied is V1, what is this voltage? V1 by 2. And what is this voltage also? V1 by 2, half of. Okay. The voltage applied across half of winding is V1 by 2. Clear? This is M midpoint. This is A taken. Now BC is V1 at an angle 0. Next CA, V1 at an angle minus 120. Next, I'm following sequence BC, CA, AB. Now AB is V1 at an angle minus 240. Balanced supply given. So that supply I indicated here, three-phase supply. Okay. Now when you give this balanced three-phase supply with this 50% tapping and here 86.6% tapping at the secondary, you will get voltages V2, V2. Angles you will get is 0 degree here and 90 degrees here. You will get 90-degree voltages. So how it is, I will show you now. Observe carefully. First complete the figure. Complete the figure. So why can't we produce directly two-phase supply? You can produce two-phase supply, but not economical, no? See, when you are operating with two-phase supply, that is not economical operation. Economical means with only two phases, cost of generators increase. So you will get more power losses. So many things we need to consider. Now again, economical power generation in power systems we have. Economically, we need to generate power. Economically, we need to transmit power, and economically, we need to distribute the power so that losses is as much as possible less. So three phase is suitable. See, don't get many doubts like this. Doubts should come, but up to some limit. But if you are keep on getting why not two phase generating, why we are not using two phase for loads, this type of doubts you should not get first. That's why it is actually consuming little more time when I read your messages. Okay, now let's see. Suppose I don't know this tapping point. So I said 86.6% directly, as we know already this. Suppose we don't know what is this tapping, where to tap, where to tap. This is A only. What is this A point it is? So I just extended here, A. This is A only. So I need to find what is this voltage, VAM. This voltage is how much? This winding from this point, tapping point to this bottom, M. How much voltage I should utilize such that these three phase voltages are balanced. These three phase voltages are balanced. How much voltage I will get? 86.6%. But how to find that is that we need to calculate. And considering primary total winding voltage V1, this is both are same transformer. What is this winding voltage? V1. So what is this winding voltage also? V1, same voltage, same number of turns, same voltage. Primary side V1, secondary side V2 for both transformers. So out of total V1, how much voltage should be VAM? That we need to calculate. This is only the last year conventional question. So they asked, prove that VAM or the primary winding of teaser transformer is having 86.6% or root 3 by 2 they given. So observe carefully now. To find that VAM, let's apply KVL in this loop. Sum of voltages in the loop must be 0. Apply KVL. KVL. So if you start from point A here, if you start from this point A, VAM plus VMB plus VBA. The sum of these three voltages must be 0 here. So I am applying KVL in this loop. Okay. Next page I will write applying KVL, then what we get? VAM plus VMB plus VBA. VAM plus vector addition, these are all. VMB plus VBA. Sum should be 0. Loop, sum of voltages in the loop always 0. So that is I applied. Now I need to find VAM. So what is VAM? Equal to minus VMB minus VBA. Okay, minus VMB minus VBA. Now I will remove that minus by considering like this. I will remove this minus. So I will write VMB as VBM. Then minus will become plus. This minus also I will remove and taking plus. VBA will become VAB. VBA will become VAB. Next, if you calculate VAM equal to, what is VBM? Observe the figure. This is B. This is point B. This is B. This is M. VBM. What is VBM value here? V1 by 2 at an angle 0. So write that VBM is V1 by 2 at an angle 0 plus VAB. What is VAB? Check. This is VAB. VAB. What is this voltage? V1 at an angle minus 240. V1 at an angle minus 240. So all of you solve this value in your calculator. How much it is? Vector addition. Use complex calculation. Take V1 outside. Then 1 by 2 at an angle 0 plus 1 at an angle minus 240. Calculate and substitute here. 0.5 plus 1 at an angle minus 240 in polar form. So this is I'm getting 0.866 V1 at an angle 90 degrees. 0.866 V1 at an angle 90. Okay. .866 V1 at an angle 90. Therefore, how much voltage should be there from A to M? This voltage should be 0.866 V1. Total voltage, how much we taken? V1, total winding voltage. But how much to be used in that 0.866 V1 only we have to use. And how much angle we got? At an angle 90, it is. And what is the main winding voltage? Observe, V1 at an angle 0. Observe, main winding primary voltage V1 at an angle 0. Primary of teaser transformer winding voltage 0.866 V1 at an angle 90. So observe now carefully why two phase, how we are getting two phase 90s. See, if the primary voltage is this one, this is EMF in this primary winding is V1 at an angle 0, what is the voltage on secondary? Some V2 based on number of turns. And what is the angle? This is also 0 or not? Yes, both voltages are in phase. EMF in this primary, EMF for secondary, both are in phase. So if it is 0, here also 0. Okay. Similarly, observe primary of teaser transformer. What is the angle you got here? 90. Therefore, secondary side you will have some voltage V2 and angle is 90 degrees. So finally, at the secondaries, you are getting voltages, same magnitude V2, V2, same magnitudes of voltage, and they are displaced by how much angle? 90 degrees or not? Yes, that is the balanced two-phase supply. So if you connect the primaries of these two transformers like this, 50% tapping in main winding, 86.6% tapping in teaser transformer primary. Then the secondary voltages are, we are getting 90 degree displacement. 90. So this is primary three-phase balanced or not? Yes. Observe, primary voltage is balanced. Secondary also you are getting balanced two-phase. Therefore, three-phase is converted to two-phase supply. So in order to convert two phase, this arrangement we have to made on primary side. Okay, how much we are using primary of teaser transformer? 86.6%. How this remaining 13.4% we are not utilizing. This is just empty. Open it is. No currents will flow. Clear? So this proof only they asked in last year ESC 20 for 12 marks. Prove that the primary voltage of teaser transformer is root 3 by 2 times of main transformer primary. Main transformer primary V1. What is the teaser transformer primary voltage? Root 3 by 2 times of that. Root 3 by 2 nothing but 0.866 V1. Okay. Hello, all of you. That 180-degree displacement you forget here. In three-phase transformer, you cannot consider 180-degree displacement. So forget about that 180-degree centigrade, 180-degree displacement. That will be there. That will be there. But in three-phase voltages and currents, you cannot take that 180-degree analysis here. You cannot consider. Forget about that. Directly take primary voltage is some V1 at an angle 0. What is the secondary voltage? Both in phase. That is EMF in both windings you can consider. EMF induced in both windings. Same only always. Whatever will come here, same will be there on secondary side. That's why we are considering 0. There also 0 will be there. Or if you take 180 degrees, there also 180 degrees will be there. Okay, don't consider here. Observe how V2 angle we got 90. This is 0. Main transformer secondary 0. Why 0? Primary of main transformer 0 degree. That's why here also 0 degree. Both voltages in phase. In three-phase transformers completely we drawn like this only. Secondary voltage, primary voltage in phase. Okay, here also same we are proceeding. V2 at an angle 0 because primary is V1 at an angle 0 degree. Here also 0 degree. And primary of teaser transformer 90 degrees. Here also 90 degrees. Both in phase. Okay, that's why 90 degrees taken. Now if you see the secondary side only, this is V2 at an angle 0 and this is V2 at an angle 90-degree displacement. So these are displaced by 90 degrees with equal magnitude of voltages. This is called balanced two-phase source or two-phase voltages. Now you can give that is to loads. Okay. So finally three-phase is converted into two-phase by using a proper connection on primary side. How to connect it is the primary of main transformer should be tapping at 50% and primary of teaser transformer having tapping at 86.6%. How do you know 86.6%? We calculated according to our three-phase voltages. So we got 0.866 V1. Okay. Why magnitude on second is same? Because we taken two identical transformers. If it is V2, here also V2 only will be the same number of turns, no? That's why. Now the important questions on this COT connection is, so the important questions are checked. Now I'm writing currents on primary side. Observe carefully. Currents. Let this is the line current IA. This is the current in B, IB. This is current in C, IC. Three phase currents. Secondary side, I'm taking teaser transformer secondary small IA, main transformer secondary small IB. Okay, main transformer IB, teaser transformer small IA. Now, if you talk individually about main transformer and teaser transformer, see main transformer, it is primary side. What is the current flowing in the primary of main transformer? IBC or not? Consider main transformer separately, teaser transformer separately, suppose. Then in the primary of main transformer, current flowing is from B to C or not? Yes, that IBC we call primary current of main transformer. Don't say IB is the primary current of main transformer. It is flowing, but IC also coming here. This is one line current, this is one line current from three-phase supply. But if you want primary current of main transformer, IBC is the primary current. Okay, but in teaser transformer primary, IA is flowing. IA. Now same IA will go in the complete winding or not? Yes. This is itself primary current of teaser transformer. Okay. Now I will take one more figure because it will become so much conjunction in this. I will take one more diagram to represent currents. Same diagram I'm redrawing. For current representation it is. .6% tapping here. Terminal A, B, C. BC is the main winding primary, main transformer primary. BC is the main transformer primary, and this is M. AM is what? Primary of teaser transformer. Primary of teaser transformer, and this is the secondary of main transformer, and this is secondary of teaser transformer. Okay. Now I'm writing only currents. Let it is IA, current IA from the supply. This is current from supply IB, and this is IC. And current in this winding, primary winding, let us consider IBC is the primary current of main transformer, IBC. And this is the secondary current of main transformer, small ib. And secondary current of teaser transformer, small ia. Okay, and 1:n2 is the turns ratio in both transformers. Now, tell me, this primary is a three-phase source only, no? Three-phase it is. Primary side we have three-phase, secondary side we have two-phase with voltages 90 degree that we have seen previously. Okay, now this primary side three-phase looks like star connection or delta connection. Three-phase means we have two connections in actual three-phase transformer, delta connection and star connection. Now this primary windings connection of these two primaries looks like a star or delta. It looks like what? Star or delta? Star. Yes, it looks like star connection. If it is a star connection, there must be a neutral point or not? If it is a star, there must be a neutral point. Now, in this primaries of two transformers, where neutral will be there? This is also one important question. Neutral is located in which winding dash? In which winding? Primary of main transformer, primary of teaser transformer. So where neutral is located? Neutral will be located. Now most of the people may say, yes, same thing I expected. Main transformer. Some of you saying main transformer, but answer is teaser transformer primary. Neutral will be located in the teaser transformer primary side. So why it is? Suppose you don't know where is neutral. Let this voltage is V1. All voltages are same magnitude. Three phase means same magnitude of voltages. Three phase voltages. Okay. Now this is line voltage. The voltage between two lines is called line voltage, right? It is V1 is the line voltage. If it is a star, what is the phase voltage in star? V1 by root 3. Line voltage by root 3. How much it is? 0.577 V1. Okay. So with respect to this value, I will start from A. This is A now. From here, I will take 0.577. I will take 0.577. This voltage is 0.577 V1. Okay, I will assume this is my neutral. I will assume. Now I need to check this neutral is stable neutral or not. Yes, I need to check. Observe here. This is A. Now VAN 0.577 V1. How can you say that in a star connection neutral point is stable? How can you say this neutral is stable neutral? Just by calculating the voltages from all the lines, no. So VAN, suppose A, B, C. The neutral is said to be stable if VAN equal to VBN equal to VCN. Then neutral is fixed or stable point. Now same thing we will check here. Now I will check. Observe here. VAN is this over. Now start from B. This is B and this is C. VAN we got 0.577. Similarly, you verify what is VBN. Start from B and move towards N. This voltage how much? 0.5 V1 it is. Okay. Now what is this voltage also? 0.5 V1 magnitude. Now what is this voltage remaining? Remaining voltage how much here? What is this total voltage we are using in teaser transformer primary? 0.866 V1 we are using. Already 0.577 is there. Now how much voltage here remaining? Calculate 0.866 minus 0.577. You will get 0.289 V1 it is. Check this value once. 0.289 V1. Now we need to check what is the value of VBN. VBN. What is VBN? Observe. V, this is B. VBN, nothing but VBM plus VMN. VBM plus VMN. 0.5 V1 plus 0.289 V1. But don't add directly. Vectorial addition. Vectorial addition. This is 0.866 V1 at an angle 90. This is total V1 at an angle 0 it is. So we have to add vectorially 90 degrees now both. This winding voltage, 90 degree displacement. So what is vector addition of 90 degree displacement? Directly root of A square plus B square. Otherwise, if you have doubt, write like this. VBM plus VMN. What is VBM? 0.5 V1 at an angle 0 plus what is VMN? 0.289 at an angle 0.289 V1 at an angle 90 degrees. Okay, now add these two. Or directly you can do like this. 0.5 V1 whole square addition root A square plus B square. 0.289 V1 square. Calculate this. How much? VBN. How much this value? Yes, almost you will get nearly 0.99 V1, nothing but that is 0.577 V1 only we get. 0.577 V1. This is also same as it is VAN. Similarly, VCN, if you find C to N, same as it is VBN, if you find this is also you will get 0.577 V1. Therefore, the voltage from all terminals to neutral is same magnitude or not? Yes. Therefore, can we say that the neutral, whatever we have placed, this is a stable operating neutral or simply stable neutral point. Okay. This is a stable neutral. Clear all of you? So where neutral is located? In the primary of teaser transformer. And one more point regarding neutral is observe. This is total 0.866 V1 and here 0.577 V1 and here 0.289 V1. If you multiply this 0.289 into 2, you will get 0.577. Nothing but total winding if you divide into 3 equal parts. This is 2 parts, this is 1 part. Then this neutral will divide the primary of teaser transformer into in the ratio 2:1. This neutral will divide the primary of teaser transformer in the ratio of 2:1. Check if you want. 0.289 into 2, you will get 0.577. This is also many times in examinations repeated question. In what ratio neutral will divide the primary of teaser transformer? In what ratio? 2 is to 1. Okay, they will give in the options 2 is to 1, 3 is to 1, or 4 is to 1, like that. So answer is 2 is to 1, it will divide. Okay. So write these 2 points in the note. Write the 2 points. Make a note of this. Note. First point. First point. On primary side. On primary side, the neutral is located. The neutral is located in the primary of teaser transformer, because people will confuse that. They will say main transformer because the name given main, so everything will be in main. No, main is given the name because total winding we use in the transformer, that is the main transformer. In other transformer, total winding we are not using, 86.6% only we are using in the primary of teaser transformer. Next, second point. This neutral will divide the teaser transformer, will divide the primary of teaser transformer, primary of teaser transformer in the ratio of 2 is to 1. In the ratio of 2 is to 1. Remember this. Now let's see some important current relations between primary current, secondary current. What are the values we get? So this relation, what is that is? This is what is the primary current of teaser transformer? IA. What is the secondary current? Small ia. Like that. What is the primary current of main transformer? IBC is the primary current. Don't say IB or don't say IC. IBC is the primary current of main transformer, and small IB is the secondary current of main transformer. Okay. Now let's write the relation between these two transformers. Important it is. See this. First, I am taking teaser transformer. Teaser transformer. Primary current, secondary current relation we need. Observe. What is the transformation ratio for currents in terms of currents? I1 by I2 is K. Or what is the K in terms of turns? N2 by N1. So actually we are writing I1 by I2 equal to N2 by N1 only, no? In terms of turns. Okay, I think everyone knows this. Same relation I'm writing now. Now, what is the primary current of teaser transformer? IA. What is the secondary current of teaser transformer? Small ia. This is equal to N2. Secondary total turns we are using, but primary side, out of total N1, how many turns we are utilizing in this? See, total N1, but we are using 86.6% only, means 0.866 N1 turns only we are using, not total N1 turns. That's why 0.866 N1. Clear why I'm writing 0.866? Because in the winding total turns we are not utilizing, only 86.6%. Okay. Next, capital IA equal to small ia into 1 by 0.866 is 1.15 into N2 by N1. N2 by N1. Now, further if we simplify by assuming IA into 1.15, because why it is N2 by N1 we removed? Because N1 equal to N2, or turns ratio is unity. Anyone? N1 equal to N2, same turns on both the sides, for example. Then both gets cancelled. No? Both are same turns. For example, we are considering this is let N1 by N2 is 1. Turns ratio is unity. Then this is the primary current. What is that? The primary current of main teaser transformer is 1.15 times of secondary current. For what case it is? When turns ratio is unity. When turns ratio is given unity in the question. If it is not unity, you have to use this equation. Suppose they given some other turns ratio and substitute here, you will get the primary current. Now here the important observation is previously in the competitive examinations, whenever particularly SAIL examination or ISRO examination, ISRO, in ISRO also previously we have question on the Scott connection. They are asking the primary current of teaser transformer. The primary current of teaser transformer is dash compared to secondary current. The primary current is dash with respect to secondary current. For the turns ratio is unity. In the options they given 2 by root 3, root 3 by 2, 2 root 3, 2. What is the answer? Primary current is dash times of secondary current for unity turns ratio. What is the answer? Yes, sir. Yes, most of you given right. Answer is 2 by root. Why 2 by root 3? Here I given with the numerical 1.15 value, but they given here like in this way 2 by root 3 by 2. So this is you have to simplify little, then you will get answer is 1.15 times. 1.15 is nothing but 2 by root 3. That's why both you should remember. The same you can also write as 2 by root 3 times of secondary current. Remember both. Okay. Now, in other way also you can get question. What is the extra current flowing in the primary of teaser transformer? How much extra current? Suppose secondary current is some 100 amperes. What is the primary current? 115 amperes. So how much extra current is flowing? 15% extra current. So this value. In the primary of teaser transformer, an additional current is flowing. How much extra current is flowing? 15% extra current compared to secondary current. Why it is extra current? Why extra current is flowing in the primary of teaser transformer? The reason is because in teaser transformer, the primary side we are using 86.6% of winding only. Due to this, we are getting that 15% high current. Due to that 15% high current. Okay. Next, same as it is for main transformer. Same as it is for main transformer. See, for main transformer, what is the primary current of main transformer? Observe IBC. IBC is the primary current of main transformer. Small IB is the secondary current. And here we use total turns. N1, N2 total we use. See, IBC divided by small IB equal to I1 by I2 equal to N2 by N1. Total turns we are using. Now, if you take unity turns ratio, what is IBC? Or first write IBC equal to small IB into N2 by N1. And if it is unity turns ratio, IBC equal to IB itself. Since N1 by N2 taken 1 example. Same as it is both we compared. Now, actually when there are same turns, what should be the current in primary and secondary? Same. This is. If the turns are same on both the sides, the current also should be same, primary and secondary. But in the teaser transformer, what is the current we got primary side? 15% higher. The reason is 86.6% of winding only we are using on primary. That's why current rating increases. Clear all of this? Remember, in the Scott connection, for main transformer, the primary current is equal to secondary current. But for teaser transformer, the primary current is 15% more than secondary current. Okay. Yes, right. Less number of turns. So remember these current relations and previous about neutral point and the percentage of winding we are using for teaser transformer and main transformer. Okay. And we are not seeing here right now about load operations, like if load is lagging, leading, or UPF, how the variations in power factor we get. So that we will see in the conventional mains examination. That is before mains, we will see that. Let's see some small questions on Scott connection. See the question. For gate, it is not required. You no need to go through this for gate examination. This question is previous ISRO question also. Yes. Complete this. After this, we take break. In Scott connection, if the turns ratio of main transformer is K, then teaser transformer has turns ratio of dash. Sometimes they will confuse in the questions. Actually, K, what we are taking K means transformation ratio, but they given wantedly if the turns ratio is indicated by K, then teaser transformer has turns ratio of dash. See, main transformer turns ratio given. Turns ratio means what is the ratio? N1 by N2 we call turns ratio. How much it is? K they given. N1 by N2 means K. Now they are asking for teaser transformer turns ratio. In teaser transformer, how many, what is the primary we are using? Total N1 we are using? No. How much we are using? 0.866 N1 only we are using divided by N2. This is the turns ratio for teaser transformer. 0.866 N1 by N2. Then what is N1 by N2 means K. So it will be 0.866 into K. In terms of main transformer, it is expressing. So 0.866 into K. 0.866 means what is that value? Root 3 by 2 into K. So answer is B. Okay. People will remember the 2 by root 3 previous one. They will put directly 2 by root 3. But check what they given here first. What they given that you need to verify. Ratio given as turns ratio given as K, and the teaser transformer turns ratio they are asking. So teaser transformer we are not using completely, we are using only 0.866 N1. That's why it is root 3 by 2 times of main transformer. Okay. Next question. Yes. Answer this one. IBC is the primary current of main transformer. Directly using the previous equations, IBC you can find directly. Okay. In the same previous, write about IA, IB also. IA, IB, IC also. Because sometimes they will ask the line currents on primary side. IA, IB, IC. See this figure. IA. This IA is flowing in all these number of turns here. IA. IA is flowing here. But from now, how this IA will flow? As it is midpoint tapping, half of the current IA by 2 in this direction, and half of the current IA by 2 in this direction. Okay. Now this is the IB direction. This is IC direction. We need IB, IC. IA is directly same. IA is IA only, no change. But IB, IC equations are there. Observe here. What is IB? Tell me. IA equal to, just now we calculated previously. What is that? 1.15 IA. And what is IBC? We got IBC. IA only, no? IB. IBC means IB. Whatever I written here, these equations. IBC means IB. IA means 1.15 IA. So IB I required IA, IB, IC required. These three current equations. IA, IB, IC we call line currents, three-phase line currents. Okay. How to find that IB, IC? Observe. IB equal to, so you need to observe this cursor carefully now. IB is this. See, IB is this. IB equal to IBC also in the same direction. See, this is IBC. This is IBC in the same direction. But IA by 2 is coming here. IA by 2 coming in this direction. IA by 2. And IA by 2 in this direction. So IB is what? IBC minus IA by 2. IBC minus IA by 2. Okay. Clear? Why it is minus IA by 2? Opposite, no? This is IB. IBC also in same direction. But IA is coming, IA by 2 is coming opposite direction of IBC. So IBC minus IA by 2. Similarly, tell what is IC? Tell what is IC? IC. To IC, IC is in this direction. But IBC is opposite direction of that. So minus IBC minus IBC. To IC, IA by 2 is coming here, IA by 2. This IA by 2 also coming opposite to IC. So minus IA by 2. These are line currents, IA, IB, IC. IA is same 1.15 IA directly will get, and IB, IC you need to write the equations. IBC minus IA by 2 minus IBC minus IA by 2. All of you got it this? So remember these equations. These are line currents. And what is IA? Primary current of teaser. And what is IBC? Means primary current of main transformer, IBC. So that IA, IBC we have seen. And these are line currents from source, IA, IB, IC. Okay. Let's see the question. See this question. Why we are taking 86.6%? So we are not taking, so we have calculated there others. See, suppose AM, A is the tapping point. I don't know where to tap. I don't know where to tap this winding. So directly I taken some point A it is. Now I calculated that AM value no using this KVL. See, VAM I got 0.866 V1. That's why we are tapping there 86.6%. If total is V1, 0.866 required means 86.6% only, no, that is for out of V1. That's why we tapping at 86.6%. Then only if you tap at 86.6% only, these three-phase voltages are balanced. Otherwise, they don't be balanced. You cannot apply that balanced voltages. Suppose you take directly V1, complete V1, then here you don't get V1. If you take directly V1, these voltages will not satisfy here. According to these three-phase voltages, we are getting 86.6% here. Clear? See the question. So after this question, we take break. So once a Scott connection is complete, then we can start parallel operation of transformer. That's why. Just read the question and tell directly the answer. Tell directly answer. The primary windings of two single phase transformers are connected as shown in figure. This is the main transformer primary. This is primary of teaser transformer. Okay. Now we need to find the voltage VRS. Where is R? This is R. This is S. We need to find VRS. So same as it is. However, I applied previously KVL. Apply KVL. VRS plus VSY plus VYR equal to 0. Sum of voltages in the loop is 0. Now we need VRS value. So VRS equal to minus VSY minus VYR. And this is, I can write VYS plus VRY. Now VRS equal to, what is VYS? VYS. This is total E1 at an angle minus 120. Now in VYS we have E1 by 2 at an angle minus 120, and this is also E1 by 2 at an angle minus 120. But anyhow, this VYS only required. E1 by 2 at an angle minus 120 plus VRY given E1 at an E at an angle 0. This is E, not E1. E it is. E by 2 at an angle 1 minus 120. This is E at an angle 0. So solve this. How much? Calculate. Root 3 by 2 E at an angle minus 30 degrees you will get. This is VRS. So calculate in your calculator. Complex. Directly also you can tell. Directly also you can tell. Because 0 degree here minus 120 degrees. 120 degree displacement means however we calculated previously in our diagram, same thing. You will get a 0.866 E. 0.866 means root 3 by 2. Only one option is there, root 3 by 2 options. Okay. So that polarities and all you neglect. No need of that polarities to solve. Directly apply KVL and solve the voltage. That's it. Okay. So take break for 15 minutes. After the break, we continue. So mostly before parallel operation, we will see briefly about switching transient first for half an hour, and then we start parallel operation of transformer. Okay, let's see first about switching transients in transformer briefly first. Then we go to parallel operation. Right, starting switching transients in transformer. What is transient means? Transient effect is what? Transient. It is a temporary effect. And when transients will take place? Transients will occur when we have energy storage elements like inductor capacitors. Mostly you will see this transients topic in the network theory. There we have RL network, RC network, or RLC networks. So there transients we will see about transients particularly there. So whenever any network, if it is having any energy storage elements like inductors or capacitors, definitely this transient effect will be there. Transient means sudden change. Suddenly it will sudden change will take place whenever switching on, or if you apply any voltage signal to the winding, some transient effect will take place. It will disappear after some time constants. We already with respect to control system point of view or in your networks also, how many time constants required to reach steady state from the starting? Once the switch is closed at t equal to 0, how many time constants are required to reach steady state? 5 time constants. In control system also we have. In order, once you given a step input, you will get step response at the output. What is the how many time constants required to reach steady state value? Yes, 5 time constants. In 5 time constant, transient state will disappear and only steady state will be there. Now, in our transformer, what we have energy storage elements? The winding itself. What is the nature of winding in transformer? Inductive nature or not? Primary side, secondary side, whatever we are using, that is inductive nature. So if you consider a transformer series, we have some number of turns, primary and similarly secondary side. And this primary we are exciting with an alternating voltage signal. Okay, primary we are giving a voltage signal V1 of some frequency F. Let us consider a switch here. Through a switch we are applying. Now what is the behavior of this winding? So we have number of turns, then that winding will form an inductive nature or not? Yes, that is having some inductance. Windings will have some inductance. So if you consider with respect to network point of view, a small RL network, let us consider RL network. Okay, RL network. Whenever a voltage signal is applied through a switch at t equal to 0, switch is closed at t equal to 0, having some RL. Now a current will flow. Now this current component is having two components again or not? One is transient state current and steady state current. So total current in the network is what? Transient state plus steady state. The total current is transient state plus steady state current. Okay. How to write steady state current equation in this network? Steady state current equation is what? ISS equal to, tell me. Let V1 equal to some Vm sine omega t. Okay, Vm sine omega t. Now what is the steady state current? Yes, Vm by Z. Z means root of R square plus XL square. That is omega L square, inductive reactance. R square plus omega L square or XL square. This is Z into sine omega t minus some angle. Current will lag that voltage by some angle. If it is sine omega t, current will lag the voltage by some angle based on the RL values. Okay. So this is our steady state current. Similarly, how can we write transient state current? Transient state. So this transient current response is C into some constant C1. Let us take C1 into e power minus t by tau. So this is, I'm writing directly. Don't ask how it is, why it is. These are all in networks transient relations. It is directly I'm writing that expressions. That's it. Steady state current equation is this. Transient state current equation is this. Transient current is the exponential current. Observe e power minus t by tau. Like this will be there. Transient current will be exponential. This is like this. The transient component slowly reduced to zero. After that, only steady state current will be there of some magnitude. That magnitude is this much. Okay. So this is transient component and this is steady state current. Transient current is the exponential component. Whenever time constant increase, suppose at t equal to 0, switch closed. After some time, means time constant. What is the time constant of this first? Time constant of a RL network is what? Tau equal to L by R. Time constant is L by R. Now, let us consider ideal case. Ideal means what is the resistance of the winding in ideal transformer? What is the resistance? Zero. Highly inductive, purely inductive nature. Ideal means purely inductive, resistance is zero. If resistance is zero, what is the transient current component? See, tau equal to L by R. As resistance zero, tau is what? Time constant is infinite. Then what is the current ITR will become? Some constant C1 into e power 1 by infinite. 0 means 1. So only C1 will be there in this. So transient current is the DC component, a constant value that is present for infinite time constant. Therefore, it is a DC current or DC component. So in ideal case, what is the transient current here? DC current, a DC component. Why DC? So if you substitute time constant infinite, because L by R is 0, infinite, 1 by infinite. What is 1 by infinite? 0. E power 0 is what? 1. Then only C1 will be there. That is a return. Okay. So you remember only these two currents enough for our analysis. Transient current is this. Steady state current equation is this. This is also not required. Just I'm giving an idea in RL network how we calculate transient current and steady state current. Okay. Now let's see the transients in our transformer, how it is taking place and what are the problems of this transient effect. See, consider this is the voltage signal we are applying to transformer winding. What is the voltage signal? A sinusoidal, no? It is varying at frequency 50 hertz. This is our supply voltage V1. Now tell me the answer for this question. Let us close the switch. Suppose at t equal to 0, at some instant at t equal to 0, I will close the switch. Whenever I close the switch, that is t equal to 0. At t equal to 0, when you close the switch, can you tell at that instant, whenever switch is closed, what is the magnitude of voltage will appear across the winding? See, this is our sinusoidal, means whenever, what is the frequency? 50 cycles per second, means in 1 second, how many cycles are going? 50 cycles. Now can you tell, now at that instant, suppose at one instant, now can you tell at that time what is the voltage, magnitude of voltage? Is it 0 voltage, or is it maximum voltage, or it is 0, or is it negative maximum, or in between positive max and negative maximum, somewhere here? Can you tell like that? Voltage signal is there, that signal is having frequency 50 hertz. 50 hertz means 50 cycles per second. So in 1 second 50 cycles are passing. Now can you tell at some instant what voltage will appear to the transformer winding? So try to understand this. Whenever I close the switch at some time t equal to 0, can you tell what instant of voltage will appear to wind? No, we cannot tell this. Or tell one more. At what instant of voltage signal it is better to close the switch? At what instant? This is also previous questions only. At what instant of voltage signal it is preferred or it is best to close switch? That is voltage 0 point or voltage maximum point or RMS voltage or average voltage. Where it is preferred to close the voltage signal? Tell me. At what instant of voltage it is better to close the switch? Okay, good. As some of you know, maybe already know that, giving right, maximum. And some of you said 0 and some of you also given RMS. The answer for this question is maximum voltage. So you have to close the switch whenever voltage signal is crossing that maximum value. Can anybody close? Suppose a task given to you. I said close the switch only when voltage is maximum. Can anybody close? So if you able to close, you are the king maker. Can you close? Can anybody close? No. No one can close. Always at voltage maximum. No one can close. How can you say that first of all, now voltage is maximum? Can you say now voltage maximum? You cannot say. No one can say this. Then how can we close the switch at voltage maximum? You can close with power electronic controllers. Okay, try it. If you are able to close, try it. We cannot close the switch at voltage maximum point. So why we need to close at voltage maximum first? First, try to understand this. Then we go to why we need to close the switch at voltage maximum point. I will show you. See, as signal is proceeding 50 cycles per second, it is changing instantaneous value. No, these are all signal means what? Instantaneous. At different instant, different values. So no one can close the switch at voltage 0 point, or no one can close at voltage maximum point, or some other values, because no one can guess what is the voltage magnitude. No one can guess. So we need to close the switch at voltage maximum point so that no transients will take place in transformer. But if you closed the switch at voltage 0 point by mistake, suppose if you closed, then you will get severe transients in transformer. That is the dangerous switching. Closing the switch at voltage crossing 0 point. That is the dangerous point. So let's see why it is. For that, I will show you first the phasor relations. See, this is the voltage signal, sinusoidal. Okay, voltage signal it is, sine wave. If voltage is sine, then if you apply a sinusoidal voltage, a current is flowing. What is that current? We call magnetizing current initially. Now that current lags the voltage by 90 degrees. With a purely inductive case, ideal case we are considering, current lags voltage by 90 degrees. Current lags voltage by 90 degrees. This is the current, magnetizing current, I. Now, where is the flux produced? So if you continue this is the current. Now, where is the flux produced? In phase with current always. The flux produced is in phase with current. Flux produced is always in phase with current. Okay, this black signal is flux. So this is already we know. If you apply a voltage, current will flow, which lags voltage by 90 degrees. So that is started from 90, and flux produced, that is always in phase with this. And then EMF induced and all we know. Now we are talking about mainly transient effect. What is the problem of this? Now observe here. If you close the switch whenever voltage magnitude is 0 here, if you close the switch at this instant, how much flux should be there in the core at that instant? Maximum flux should be there in the core to satisfy this relation. This is our actual relation, phasor relation, right? It is current lags voltage by 90 and flux is in phase. These are all. If you close the switch at voltage 0 point, the flux required in the core is maximum flux minus phi m. This much flux should be there in the core at that instant. But tell me first, before closing switch means, before closing means how we represent t equal to 0 minus. At t equal to 0, if you close, at t equal to 0 minus 0 plus, what happened? We need 0 minus means open. Whenever switch open, is there any flux in the core? No flux, because no currents in the winding, no flux. Flux is 0. Now, if you close the switch at t equal to 0, just after closing switch at t equal to 0 plus, suppose switch closed, just after closing the switch, just after closing the switch at t equal to 0 plus, tell what should be the flux in the core. So we have one theorem. The theorem name is constant flux linkage theorem. Constant flux linkage theorem. Now, what the statement of this theorem is? It states that the flux in the core remains same just before the switch is closed and just after switch is closed. Suppose at t equal to 0, switch closed. Then the flux in the core remains same just before closing the switch. Just before means 0 minus. So at 0 minus, what is the flux in the core? 0. So just after closing the switch also, flux in the core remains same or constant. So 0 only should be there in the core. If you close the switch at t equal to 0, just before closing, whatever is there, just after closing also, same flux should be there in the core. Before closing means 0 flux. After closing also 0 only there, because once you close the switch, current is flowing, but immediately no core can produce the flux maximum value. Observe now the phasor relation. Observe this. If the switch is closed at voltage 0 point, how much flux should be there in the core? Maximum flux should be there in the core. You take any voltage 0, take this voltage 0, then how much flux should be there? Maximum. That may be positive max or negative max. We don't want that sign. We need maximum. That's it. If you close at voltage 0 point, the flux required at that instant is maximum. Is any core will produce maximum instantly? No, practically not possible. So as it is not possible practically, a severe transient effect will take place if you close the switch at voltage 0 point. Now let us check voltage maximum point. This is the maximum voltage point. These are maximum voltage point. Now at maximum voltage point, how much flux should be there according to this relation? 0 flux. If you close the switch at voltage maximum point, what is the flux required by the core? 0 required for this relation. So 0 possible or not? Yes, 0 only there already. 0 is possible. So we don't get any transient effect. So when transient effect is taking place, mainly whenever we close the switch at voltage 0 point. Why it is taking place? At voltage 0 point, we require maximum flux, but no core will produce. That's why transients will take place. So what happened? We will see. Suppose if the switch is closed at voltage maximum point here at this instant, then how much flux is required? 0 required. 0 possible or not? Yes, possible. That's why you don't get any transients. It will start from 0 only and proceed normal relation, and you don't get any transient effect. Okay, first write these 2 points. Write these 2 points first. First, right? The transients in transformer depends on the transients in transformer depends on the transients in transformer depends on the instant of instant of voltage signal applied to the windings. The instant of voltage signal applied to the windings. Now, first point. If the switch is closed, at voltage voltage signal crossing maximum values, maybe positive max or negative max, anything that is. If the switch is closed at voltage signal crossing maximum value, the flux required in the core is, how much flux required at that time? 0, comma, this is possible or not? Yes, 0 possible practically. The flux required in the core is 0, which is possible practically. Hence, no transients takes place. So there is no problem of the switching. No transients here. Transient free switching it is. Next, second point. If the switch is closed, at voltage signal crossing 0 values, then the flux required in the core is how much? At voltage 0 point, how much flux required? Maximum, which is not possible practically. Which is not possible practically. Hence, transients will takes place in transformer. Transients will takes place in transformer. Now, what is the transient effect? You will see. Transients will takes place in transformer. Okay. Now see, what are the transients? What is the problem we are getting with this? So if you close the switch at voltage 0 point, how much flux is required? Maximum is required. But no core can develop. According to the theorem statement, we are proceeding. What is the theorem? According to this theorem, it states that the flux in the core just before switch is closed and just after switch is closed remains constant. Before closing, what is the flux in the core? 0. So 0 only possible after closing also. But maximum no core will produce. Then it will deviate. So maximum it cannot produce. It will produce from 0 only. So it will deviate. How it will deviate is observe here. However, we have the total current is what? Transient current plus steady state current during transients. Total current in the winding is sum of transient current plus steady state current. Similarly, total flux in the core is transient flux plus steady state flux. And whatever we have drawn here, this is steady state. Whatever signal we are drawing, that is steady state signals. Now we need to find what is the transient component. Tell me first. Suppose at t equal to 0, I close the switch. Then at t equal to 0 plus, what is the flux in the core? Total flux in the core should be 0 only. But actual flux signal is this equation. Now equating total flux equal to phi tr plus steady state flux. Okay. Now total flux should be 0. And this is equal to transient flux. And how much flux should be there at this point at t equal to 0 here if I close the switch? How much steady state flux? Maximum flux minus phi m, minus phi m. Then what is the magnitude of transient flux from this? Calculate this, send it left side, it will be phi m. This is the magnitude of transient flux. Transient flux is this much. Now a transient flux is there, phi m. Now this phi m, this transient component is a DC component or not? Yes, DC component. Why DC? Just now I given in previous here. For DC resistance, now for ideal case, what is the resistance? 0. Time constant is infinite. Now what is the transient current we got? Constant C1. Transient current is constant value. Constant value means DC current, that is. Like that, the flux also, the transient flux is maximum flux, and that is a constant value. Maximum means this is minus phi m. Now I'm considering a DC component plus phi m. This is minus phi m, this is plus phi m. Now this is DC. DC means take a constant value. Up to what time? Infinite. For ideal case. If it is practical case, it is not infinite. For some time constant, it will be there and then slowly decays to 0. Practical case, this phi m decays to 0 after some time constants. But ideal case, infinite. Ideal case, r equal to 0, tau equal to, tau is what? L by r, 1 by 0, infinite. So time constant is infinite time constant. Now, considering to draw the resultant flux, transient flux and steady state flux. Observe now. Observe carefully. I will take with. So I will take other color. Is it visible? Okay, right. So I will take this color. Observe. This is our resultant I am drawing. Now the total flux is 0. So it starts from 0. Sum of transient flux plus steady state flux. Transient is plus 5 max. Steady state is minus 5 max. 0 it is. Sum of these two. Total flux is sum of these two fields. 0. Now at this 90-degree, steady state flux is 0, but transient flux is maximum phi m. So it will be up to here. Okay. Sum of transient and steady state I am drawing. Observe carefully. Now at 180 degrees here, at 180 degrees here, steady state flux phi m. This is also phi m. What is phi m plus phi m? 2 phi m. Phi m plus phi m, 2 phi m. Next, at this is 180, this is 270. At this 270, steady state phi m is 0, but transient is phi m. Then you will get this much phi m again. And again at this angle here, this is minus phi m, this is plus phi m, so you get 0. Okay. Again at this angle, this is phi m, steady state flux is 0 and transient is phi m. And if you draw, you will get like this. So like this continuously you will get. And how much magnitude you are getting? The peak of the flux. The peak of the flux you are getting double the maximum flux. Double the maximum. This is 2 phi m. 2 phi m. Double the maximum. So this color, whatever we have used previously, this color is what? Flux in transient. Flux produced whenever switch is closed, whenever voltage crossing 0 point. If the switch is closed, when voltage crossing 0 point, the flux produced waveform is like this. Okay. See, ideal case, it is continuous coming, but practically it is not continuous. It will reach double the maximum, and after few cycles, just 2-3 cycles, just after 2-3 cycles, it will come normal steady state again. Normal steady state practically. Okay. Practically we have transient. For practically transients takes place for short time, that effect will be there, but not for long time, no? That may be any condition, loaded condition or unloaded condition. uh, See, this green line is what? This is the flux in transient condition. This green line indicates transient flux, and this black line indicates steady state flux. And whatever flux we have drawn, total flux, sum of transient plus steady state. Okay. Now finally, what is the effect of this here? Whenever switch is closed at voltage 0 point, so listen carefully. Whenever switch is closed at voltage 0 point, the flux required in the core actually minus 5 max, but practically it cannot produce. So it will deviate now. How? Actually flux should be 0. So for that it will produce a DC component of transient flux here. Then sum of these two is what? 0. It starts from 0. It starts practically, the flux will start from 0 only, and then it will reach double the maximum flux. Phi m is maximum flux, but it will reach during the transient double the maximum flux for few cycles, 1 or 2 cycles, and then again steady state it will come practically. Okay. Now this effect in transformer we call doubling effect of transformer. Doubling effect of transformer. See, actually these are all you don't require, only for mains conventional examination. Actually I have to give this, but some people asked how it is becoming double and all. That's why I given these equations now. Otherwise, theoretically you remember only one point, only the 2 points. What is that? If the switch is closed at voltage maximum point, there is no transients takes place. Next, second, if the switch is closed at voltage 0 point, the flux required by the core is maximum, but no core will produce maximum at that time. So it starts from 0 and it will reach double the maximum flux. That effect in transformer we call simply doubling effect of transformer. After a few cycles, again you will get normal steady state. Whatever we have drawn the previous voltage, current, flux, that steady state signals you will get. Okay. Transient, how much time is? Approximately 5 time constants. Time constant, how to find? L by R for a RL network. You should know that L and R values. Then you will get time constant and multiply here. That is in just milliseconds only. You will get 5 time constant. Okay. So right here. Right. Make a note. Note. Just write the 2 important points. Whenever switch is closed, whenever switch is closed at voltage crossing 0 points, voltage crossing 0 points, then the flux required is maximum. The flux required is maximum, but no core can develop, no core can develop maximum flux instantly. Maximum flux instantly means at t equal to 0 you closed. At the same time, how maximum flux? No core will produce. No core can develop maximum flux instantly. So it will deviate, it will deviate and reaches double the maximum flux, and reaches double the maximum flux, which is called, which is called doubling effect of transformer. Doubling effect of transformer. Okay, this is the main problem of transient, doubling effect. Now what is the consequences we get due to this doubling effect? We have to say. Okay, let's see what are the effects of this doubling effect of transformer, or drawbacks of doubling effect. Right, side heading, drawbacks of doubling effect. Yes, ideal case, it never comes to steady state. Means transient state continuously there now up to infinite. Yes, but ideal is possible, not possible. For our analysis, every time we consider ideal, because practical directly we cannot analyze theoretically, because without transformer, how can you say practically? That's why ideal we assume and we will apply after that. Okay. It's heading drawbacks of doubling effect. Drawbacks of doubling effect. See, particularly in this topic, uh, in very long back in GATE examination, we have the question in very long back. But from lastly up to mostly 10 to 15 years, if you fetch, we don't have question on this topic in GATE. But in engineering services, sometimes we are getting, and for competitive examinations, mainly it is important. This in competitive exam also, they don't ask about doubling effect and all there. They are asking previously in some examinations only at what instant switching of transformer is best. Voltage 0 point, voltage maximum point, this question only. And one more question is there. In magnetic inrush current, which is the most dominant harmonic? So that question. So that is also we will see in this point, drawbacks. Only these two questions repeated. Right. Drawbacks of doubling effect. First point. See, doubling effect is what? The flux in the core becomes double. Double the maximum value. Maximum flux in the core already there, but now it is double the maximum. That is called doubling effect. So whenever flux is doubled, what happens to density? What is the flux density? Flux per area. If flux in the core is double, density also double or not? Yes. Then this is called deep saturation of core. Saturation, if little flux increases above maximum saturation, now it is deep saturated, double. Then due to this double the maximum flux, as flux density also almost double, the transformer will draw very high magnetizing current. Very high magnetizing current. This current we call magnetic inrush current. Magnetic inrush. Inrush means what? Sudden increase in any value we call inrush. Sudden increase, that is inrush. So magnetic inrush current. Suddenly current becomes very high for a short time, but not for long time. Suddenly increase and come back to again normal for short time. That is magnetic inrush current. And the shape of this magnetic inrush current, if you draw, it will be like this. See, if you observe our diagram also here, see whatever flux we are getting, this flux is symmetrical or unsymmetrical? Symmetrical means positive, negative should be same. But here, what we are getting, only positive halves we are getting. This is unsymmetrical. Flux, we are getting unsymmetrical shape. So what is the corresponding current also? Unsymmetrical. And the shape of current will be approximately like this. So after a transient period, let up to here transient. See, very high current, magnetic inrush current for short time and immediately decreases. And then this is transient period. This is transient period. And this is steady state. So practically it will reach steady state, no doubt. But during the transient time, transient means just fraction of second it is. Fraction of second only the transient effect. Now, what is the shape of this magnetic inrush current? Is it symmetrical? No, unsymmetrical. If a signal is unsymmetrical, what are the harmonics in that? Previously, I given in the Fourier series analysis 2 points there. If a signal is symmetrical, what is the harmonics in that? Odd. If a signal is unsymmetrical, then what are the harmonics? Both odd and even. That is 1, 2, 3, 4, 5, and so on. All the harmonics. So which is the dominant in this? Second harmonic is the dominant. Means this effect is more in this. Second harmonic is more. After fundamental, whatever is there, that is the dominant harmonic. But previously we have seen magnetizing current, peaky wave. Which current is dominant in the third harmonic current? So these two currents generally people will confuse. Magnetizing current, magnetic inrush current. When magnetic inrush current? During switching, transient condition only it is. Magnetizing current always. Magnetizing current always present. But magnetic inrush current will flow only during switching transient condition. And after steady state, there is no magnetic inrush current. Now, why this current is very high? Observe with the graph I will show you here. Actually, what is the variation of flux with the current in every magnetic material? In every magnetic material. See, if current increase, flux in core also increase. If current increase, flux increase. And whenever current increase, flux increase at one particular value of current, almost this is maximum flux. This is the maximum flux, and this is corresponding current to this. This is the normal magnetizing current, small current. So our maximum flux, whatever we are writing in equations regarding that, this is our magnetizing current. Very small value it is. But during this doubling effect, what is the flux in the core? Double. Double means where it is? This is maximum. Double means somewhere here. So much distance. So this is also not double. Double means so much, almost double than this. But approximately I'm taking here, let it is double the flux. If it is 2 phi m, what is the current required? Very, very high or not? This much magnetizing current required. Very, very high. Because once every core is saturated, once if any core is saturated, after that saturation point, flux increase is negligible. Flux is almost constant, slight increase, slight. But what is the increment in current? Very, 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 very high. That current we call magnetic inrush current. Now, tell me, is there any damage to transformer due to this magnetic inrush current? Any damage? Is the winding will damage? As it is very high current, generally people will think that yes, it will damage the windings, but it won't damage the transformer winding. It won't damage. Why it won't damage? For how much duration this current is present? Transient duration. That is in fraction of second. Fraction of second it will eliminate automatically. It will disappear. Now, if a current, whatever, if a high current also present for very, very short time, is the winding will damage? No, it never damage. Tell me winding when will damage? When windings will damage? If high current present for long duration. See, windings will damage due to heat or temperature. If temperatures are very, very high, copper wire will melt. So temperature depends on only I square or copper loss depend temperature depends on only I square or no, it depends on time. I square or copper loss taking place, but how much time? That is important. If the time is or if the high current present for long time, then heat also increases. But here magnetic inrush current, high current, no doubt, high current. But how much time it is? Just for fraction of second. Then this small time will not overheat the winding. It never overheat. Then where winding will damage? So this you can observe in transformers practically beside, that is in your street also, wherever transformers is located during night times only. During night time you can observe this inrush phenomenon. How you can observe is if you nearby the transformer, suppose there is no power at that time in the night time, suppose there is some power cut off. Okay, you are outside nearby transformer. Suppose if you are watching at that time, Suppose at that time when you are watching, power came. If you watch near to the transformer, there you can observe some small spark immediately will come and disappear. For fraction of second, it will come and disappear. That is the magnetic inrush current. Why it is flowing? Mostly whenever power come to transformer or supply coming to transformer, that is switching instant, switching only, that is. So during that time, most of the cases, when transients will not take place, whenever you close the switch at voltage crossing maximum values. But is it happen every time? No, may or may not happen. But mostly you can observe that magnetic inrush current during night time only. That small spark suddenly will come and disappear. But no damage to transformer. Power will come as usual again. Okay. So you can observe only during night time whenever there is power cut off and power is came back. So that time. So we no need to protect the transformer from magnetic inrush currents. But sometimes a relay will operate. Why? Sometimes a relay may operate due to the sudden high currents. Relay should differentiate between magnetic inrush current and fault current. So for what relay should operate always? Fault current. For fault current, high currents. Whenever high currents is flowing, then relay should operate, but not for magnetic inrush current. But sometimes there is a chance of mal operation of relay. We call it is mal operation. Mal operation of relay takes place. Mal operation means unnecessarily relay will operate. Whenever there is magnetic inrush current, relay may operate. Now we need to protect, we need to provide some mechanism for this, so that for magnetic inrush current, relay should not operate. For which current relay should operate? Only for fault currents. So how it is protected, you will know clearly in the differential protection. Power system protection. What is the protection scheme we use for transformer for internal faults? Differential protection system we use. So there you will see about second harmonic restraining coil. Second harmonic restraining coil is there in that relay. Okay, so about that you will see clearly what is the purpose of the second harmonic restraining. So what the second harmonic restraining coil will do is, when there is magnetic inrush current, in that second harmonic is there or not? Yes. So this coil will sense the second harmonic signal. Once there is second harmonic signal, it won't allow relay to operate. Relay will not operate because magnetic inrush current will not damage. So no need to operate the relay at that time. For what relay should operate? Only for fault current, which are very high current. Only for fault current relay should operate. So to protect the unnecessary operation of relay due to magnetic inrush current, we will use the second harmonic restraining coil. So we are not seeing all clearly here, that you will see in protection only about this protection system. Okay. So write one point. Write one point. Due to double the maximum flux, due to double the maximum flux, the transformer will draw a very high magnetizing current. The transformer will draw a very high magnetizing current called magnetic inrush current. Called magnetic inrush current. Called magnetic inrush current, comma, in this second harmonic is the most dominant. Second harmonic is most dominant. This is second harmonic is most dominant. Make a note below this. Note. This magnetic inrush current, this magnetic inrush current will not damage the transformer windings, this magnetic induced current will not damage the transformer windings since it is present in the winding for a fraction of seconds. It is present in the winding for a fraction of seconds. Okay. Next, this is one drawback of doubling effect. Let's see one more drawback. One more drawback of doubling effect. Second one. See, the other drawback of this doubling effect is whenever flux in the core is double, what happened? We know that EMF induced 4.44 phi m BA we are writing. In place of that, I am writing flux phi m N1 or N into F. If it is even, N1 into F. Now observe, from this EMF induced in the windings always proportional to the maximum flux value. Okay. If flux is double, EMF induced in windings also double or not? Yes, the EMF induced in windings also double. Whenever voltages suddenly increase, double the voltages induces very high voltage. Due to that high voltage, the insulation of winding will damage or not? Insulation of winding will damage. So insulation means not insulation between winding and winding. Don't think that. Suppose previously we have seen placement of winding. First core insulation, winding, insulation, winding. So I am not saying between now insulation between windings. I am not saying that insulation. If you observe copper wire, see this is copper wire now, like a coil. Copper wire it is. If you observe on this copper wire itself, there is a insulating coating on this wire itself. There is a thin insulating coating will be there on this copper wire. So I am saying about that insulation. If voltage is high in the winding, high EMF induced, suddenly double the rated voltage, then insulation of windings may damage. If insulation is damaged, what is the problem? Suppose this turn and adjacent turn, insulation damage. Now two turns short circuit. Actually, if you place one over other any number of turns, they don't short circuit because insulation is there. Every copper wire is having insulation on it. But once insulation is damaged, these two turns will act as short circuit. This is short circuit. Once these are short, these two, sometimes they may open, or sometimes as they are short, there is no turn concept. They shorted directly. As number of turns is reducing, your overall EMF in the steady state will reduce. But anyhow, we have some protection system for this. We have some protection. In order to withstand that high voltages induces suddenly, we will provide some extra thickness of insulation for these end turns, plus or minus 5% end turns we call. For both primary and secondary, for both primary winding, secondary winding, end turns, top and bottom end, 5% we take, because totally to provide insulation is cost increase again. That 5% end turns, here we will provide some extra thickness of insulation we will provide to withstand any high voltage. Extra thickness of insulation is provided to withstand from high voltages. Okay, then why end turns only? Because as it is a transient effect, which because of transient effect may be positive, that is topmost and topmost turns or bottommost turns may affect. Why? Whatever signal we are giving, do you know positive cycle always will appear at whenever switch is closed? No. Whenever switch is closed, you may get positive half or you may get negative half. So based on that switching, any end, maybe top end or bottom end, may affect. For that end turns, we provide some extra thickness of insulation. Okay, write this point there. Right. due to doubling effect, due to doubling effect, the EMF induced in the winding will also doubles. The EMF induced in the windings will also doubles, comma, which may damage insulation of windings, which may damage insulation of windings, which may damage insulation of windings. Hence, to protect the windings, to protect the windings from high voltages, to protect the windings from high voltages, plus or minus 5% end turns, plus or minus 5% end turns are provided with extra thickness of insulating material. Plus or minus 5% end turns are provided with extra thickness of insulation. Okay, so anyhow, in practical transformers, these transients, whenever power is going cut off to transformer and again come back, then definitely that is switching action. So no problem to practical transformers. We will take the arrangements, whatever protection is required, we will provide to transformer. So whenever any number of times if power is going and coming back, there is no problem at all to transformers. Okay. Interturn fault due to improper heat dissipation. Suppose heat in the winding is not dissipating uniformly. Suppose at one of the turn heat is very high, that turn may get insulation fault or insulation damage, short circuit may take place or open circuit may take place. Okay, let's see some previous question on this. See the question. Magnetizing current in a transformer is rich in dash. This is magnetic inrush current. This is not magnetic inrush current, magnetizing current only. I mu. What is the shape of I mu practically? In a transformer required peaky wave. If I mu is peaky, flux is flat top, EMF also. Flux E. If current is peaky, flux is sinusoidal, EMF in the winding also sinusoidal. Okay, practical case. So magnetizing current is peaky wave. Peaky wave means what are the harmonics? One odd harmonics, 1, 3, 5, 7, and so on. So third harmonic is dominant in this. Next question. If it is given magnetic inrush current, then what will be the answer? Second. But anyhow, second is not given. Take care of that. What is answer? A single phase transformer is to be switched to supply to have minimum inrush current. Minimum is we don't want that inrush current. Minimum inrush current means what? Magnetizing current only, not magnetic inrush current, small current. The switch should be closed at dash. So where best to close the switch? At maximum supply voltage. Okay. You should close the switch whenever voltage crossing maximum value. If you close at 0, inrush current will flow. That is, transients will take place at voltage 0 point. Okay. Don't confuse in this type of questions. Theory questions, easy questions, but mostly chances to do mistakes in this type of questions only. Okay. Next. Let's Let's see now about parallel operation of transformers. Next topic, parallel operation of transformers. Parallel operation you will get in generator, alternator also, alternators. Whatever the power we are generating using different power plants, in each power plant again we have some number of alternators, generators, maybe two generators, three, depends on size of the power plant capacity. Okay, all these power plants are all these alternators we are operating in parallel through a common grid. So they will send power to grid. From the grid again we will take the power to the distribution side. Like the transformers also we are operating in parallel. First, let us see what are the advantages of operating transformers in parallel. Right, advantages. Same advantages again in alternators also you will see. Same advantages, whatever we will see in transformer here. So they are, see, first one. Due to parallel operation of this transformer, the first advantage is the reliability of power supply increase. Reliability of power supply increases. Okay, reliability of power supply increases. What is meaning of reliable power supply? Reliable means what? Reliable. So I will give example to understand all these points very clearly. Observe. Suppose there is no parallel operation. Assume that no parallel operation we have. There is no parallel operation concept. Then only one transformer is there. Okay. So there is a transformer and there is some load. That's it. See, initially I have a transformer capacity 10 kVA. Now it is supplying a load of 10 kVA. Okay. Now after some months, maybe 6 months or 1 year, let us check. Definitely load will increase or not? Yes. Day by day, also load is increasing. So let us take your home itself. In your home, whatever is there from 2 years back, whatever electrical devices or electronic devices, same is there now also, increases or not? Yes, definitely loads will add. As load is increasing, let now it becomes some 12 kVA. The load changes or increases to 12 after some time. Now, can we supply the same load from 10 kVA transformer? No, because capacity of transformer is up to 10 only. Then 12 kVA you cannot supply. If you supply, it will be overload. Heat is very high, it may damage. So it is not preferred. Then what you have to do? Then throw this transformer outside or put this transformer outside 10 kVA. Just throw it out and buy a new transformer of rating 12 kVA. Now you can supply that 12 kVA like this. Again in future some load increase, total load becomes 15 kVA. Again throw this outside, buy a new transformer of rating 15 kVA and supply it. Is it reliable? Is this reliable? No. So if there is a parallel operation, what we can do? So 10 kVA transformer supplying 10 kVA load. Suppose there is a parallel operation availability for us. Now what we do? Suppose load increases to 12. Now what you can do? You no need to throw that old transformer outside, keep as it is and just add one more small transformer 2 kVA. You also add some small transformer 2 kVA. Now supply 12. Like that again load increases to 15. Now you also add a small transformer again, just small 3 kVA and total 15 you can supply. Like that, this is reliable power supply to the consumers. But this is not reliable. Every time you are keeping the old one outside and buying new one and large transformer. Cost increases, size increases, maintenance increases. But here this is advantage. When there is parallel operation, if load capacity increasing, You also just add additional transformers with existing transformers. No need to remove the old transformers. That is called reliability. Okay, this is our first advantage. Reliability of power supply increase. Clear? Good. Next, second advantage. Yes, continuity. So everyone can say easily this, right? That the continuity of supply is possible. Continuity of supply to the loads. Supply to the loads is possible. So this is everyone knows. If there is no parallel operation, one transformer supplying a load. Okay. Suppose that transformer got a fault. Transformer got a trouble or fault. So once it is a fault, we will remove supply to that. Then is there any supply going to the load? No, that is power cutoff. But if there is a parallel operation, what we can do? Suppose in your street a transformer fault takes place. Now you can get still power supply from some other transformer in some other street. Like that, they can maintain or they can give continuity of supply to the loads when there is a parallel operation. But single transformer not possible. Okay. Third, right, third one, the efficiency of transformers increases. The efficiency of transformers increases. How efficiency will increase? Yes, by proper load sharing, you can increase the efficiency. Let's see the example. Suppose there is a single transformer, I will take again. There is a 10 kVA transformer supplying a load of 10 kVA. Okay, no parallel operation. First, I will take without parallel operation. Now observe, when efficiency of transformers generally high, when transformers will give high efficiency in the numericals, we observed some x fraction 70% or 80% or 85% in this range. Transformers will give high efficiency in the range 70 to 90%, nearly that full load conditions. So observe here, 10 kVA transformer supplying load 8 kVA means high efficiency only. Yes, this is good. But let us consider on the same day, the load again reduces to some 4 kVA because load will be not same throughout a day. Load will change. If the load is now become 4, same transformer supplying 4. Now what is the efficiency of same transformer? Reduced. Less than half full load. 10 kVA transformer supplying only 4. So efficiency is very less. But if there is a parallel operation, there is an advantage. What is that? In parallel operation, we never take single large transformer. So in place of that 10, I will take two transformers operating in parallel, 5 kVA, 5 kVA. Now the combination is supplying a total load of 8 kVA. Then how much each transformer supplying in that? 4. This is supplying 4 kVA. This transformer also supplying 4 kVA. 5 kVA transformer supplying 4 means 80%. So what is the efficiency? High. Now in the same day, load reduces to 4 kVA. Whenever load is only 4 kVA, then is it required to operate two transformers still? No, not required. Then only from this transformer, I will give supply to this. Then what is the efficiency of this transformer? Still you are maintaining high only. So like that, with proper sharing of load in parallel operation, we can improve efficiency of transformer. But when there is single transformer, not possible. Whatever the load, the transformer has to supply. That's it. So efficiency is low for this type of cases. Okay. Next, last advantage. Write the advantage. Advantage, that is the size and cost of standby transformer reduces. standby transformer reduces. The size and cost of standby transformer reduce. Standby means what? Standby, nothing but spare. Spare transformer cost will reduce. Where we have spare transformer? So in your street, have you seen one transformer is supplying and beside that any spare transformer have you observed? No. This standby transformers mostly in the street level we don't have. In the substation level, that is also in some substations, not in every substation. Wherever the substation connected with maximum number of loads, there only we have standby transformer. What is the need of standby or spare? What is the need of spare transformer? Suppose if your transformer supplying power to load, suddenly some fault occur. Now immediately we have to replace some other transformer in place of that. For that we need a spare. That is a spare transformer. So if there is no parallel operation, suppose there is no parallel operation, a 10 kVA transformer supplying 8 kVA load. Suddenly some fault occurred in this. Now if you want continuity to the load, you need a 10 kVA as a spare or not? Yes. Whenever it is fault, remove here and replace this. But if there is parallel operation, observe second case here. When there is a parallel operation, if there is a fault in one of the transformer, what is the spare required? 5 kVA you need spare. No need of 10, only 5 is enough. Then remove this transformer and replace here. So what is the cost and size of this transformer compared to the 10 kVA transformer? Reduces. Now don't tell if both are damaged, 5 plus 5, we need 2 transformers. Okay, don't say like this. That is rare case. Generally any one transformer may get fault, but both getting fault means that is rare case. Clear? So these are some advantages of parallel operation of transformer. Not initial cost may be little increase, because if you take single transformer 10 kVA, two transformers 5 kVA, yes, maybe according to you, some initial cost little bit increase, because two different codes, two different tanks. So different tanks means little oil level also increase in that, but little initial cost. But what is important in distribution or transmission? Initial cost important or maintenance, running cost important? Running cost important for us, not initial cost. That's why we need to take care of that. 5 kVA, 5 kVA, maybe initial cost increase, but maintenance cost is reduces. Okay. Reliable means giving supply to the loads or giving power supply to the loads with low cost. So with the single transformer case, there is a problem. Whenever load increase, you need to take new transformers every time. That is not reliable. But if there is a parallel operation, you no need to remove the previous transformers. When load capacity increase, you also install one more small transformer that is in parallel. That's why reliability it is. Okay. Spare means additional, just like in vehicles, stepney tire we use na additionally. Why we use that? For readily replacement, like that. Okay, right. The important in parallel operation is conditions for parallel operation. Let's see that. Setting conditions for parallel operation. Conditions for parallel operation. So in parallel operation, if you get any question, you may get directly from conditions, or there is only one type of numericals. For GATE and engineering services prelims, There is only one type of numerical in parallel operation. That is, they will give two transformers data and some load. How much each transformer sharing? Load shared by two transformers. How much transformer A sharing? How much transformer B sharing? Only this question if you get numerical. Otherwise, theory question directly from conditions. Okay, only these two chances. And for conventional, you will get numerical questions mostly in conventional. Those who are engineering services in conventional, there is one more case, that is I will explain in the mains only, because that questions are, each question will take here minimum 20 minutes to solve, minimum 20 minutes. But in objective type we never get that questions. Write the questions, write the conditions. First one, here we have two types of conditions again: necessary conditions, desirable conditions. What are the necessary condition? Desirable. Necessary means what? Compulsory, it should satisfy. Desirable means what? Desirable, yes, it should satisfy, but if little variation also there, we can operate. So I will give clearly both conditions separately, right? Necessary conditions. Necessary conditions. Right. First point. First, suppose if you want to operate two transformers in parallel, the necessary condition is voltage rating of two transformers. Voltage parallel means which one must be same in parallel? Voltages. In parallel always voltages must be same. That may be generators, that may be transformers. Anywhere you will get this condition. Voltage rating of two alternators or two transformers must be same. So write that condition. The voltage rating of two transformers, the voltage rating of two transformers must be same. Must be same. That is, let transformer A voltage rating 400 volts by 200 volts, and transformer B also should have almost same rating, 400 by 200, primary and secondary. Okay, same voltage rating for two transformers. Next, second condition, two transformers should have same voltage rating. Today the class is up to 7 p.m. only, because after 7 I have another class. Yes, Jadhav, you can prelims, you can, if you are applied, you can attempt. Okay, up to 7 only we take today. Mostly conditions we will complete today itself. And by tomorrow, our last day for transformers, and 5 to 9 p.m. So if parallel operation, if anything is left, we will see that remaining, and then completely auto transformers. Complete transformers will complete by tomorrow with auto transformers. After 7, class is not to your batch. That is for another. So I don't know when again you have machines. So I don't know, Vishnu. Right, voltage rating of two transformers must be same. First condition. Second, the very important, the most important condition is this. If you see in any question this condition, that is the first choice you have to prefer anywhere. So the condition is right. The polarity of two transformers, the polarities of two transformers, the polarities of two transformers should be same. The polarities of two transformers should be same. Let's see what is that polarity. So what is the problem if polarity mismatched? Very important. If you see in any question which condition is the necessary condition, means suppose all conditions are there, but first preference is polarity only, no doubt in this. So I will tell what is the reason why that much important is. With example figure I will show you this. See, let there are two transformers A and B connecting in parallel like this. Transformer A, primary winding, secondary. Transformer A, for example, 400 by 200. Transformer B also same, 400 by 200. Same voltage rating is there. Now let's see about polarity. What happened if by mistake wrongly connected? Observe this. This is transformer A, transformer B. And before connecting in parallel, what we have to do? Polarity test. So polarities are marked. So polarities are marked like this. Okay, like this polarities are marked on two transformers A and B. Now we have to join in parallel. How? See, suppose primary side, this dotted terminal of transformer A, I am connecting to this wire. Now go to transformer B. This dot you should connect to the same wire. Dot dot should join, and this is undotted terminal. Connect to another wire, and this is undotted. Connect to another wire. Similarly on secondary side, this is dot. Connect to this wire, and this dot for transformer B dot is here. Connect this is here, and remaining undot connect to another wire. This is the correct polarity connection. Dotted terminal should be connected to same wire. Undotted terminal should be connected to same wire for both transformers, primary side and secondary side. Now what is the voltage here? 400. What is this voltage? 400. This is 200. This is 200. According to our example we taken. Now observe, dot of transformer A connected to dot of transformer B. Means dot dot when you connect, this is additive or subtractive? Same polarities when you join, what happens? Subtractive. Then 400 here, and this is 400. 400 minus 400. What is the voltage, resultant voltage? 0. Therefore, is there any circulating current between the two primaries? No, 0. So this is the best parallel operation. Now let's see what happened if by mistake polarity wrongly connected. Now I will change. Observe. Observe this. By mistake, transformer B polarity is wrongly connected. Like this. Observe. Dot of transformer A is connected with the undot of transformer B. Polarity is wrongly connected by mistake. Now check. This is dot. This is undot. Means dot connected with undot means additive or subtractive? Additive. So 400 plus 400. Then what is the voltage across the two primaries? So 800. So there is a circulating current of 400 plus 400 divided by impedance of transformer A ZA1 plus transformer B impedance primary side ZB1. Now due to that, a very high current will circulate. Immediately your both transformers will damage. So for why it is, how current is flowing? See, from this dot, let current is coming like this, and it will flow in this direction, and through this it will enter into other winding. This is the path of current continuously. A very high current will circulate between two primaries because you wrongly connected. Okay, polarity is very important. If by mistake polarity mismatched, very high circulating currents will flow. Then immediately your transformer windings will damage. Suppose if you by mistake connected, and after a small time is, let us allow for 2 minutes or 3 minutes, high current is present for 3 minutes, loss is very high, heat generated very high, the windings may damage due to that. Okay, so take care of this. So always we should connect with proper polarity. Dot should connect with dot, undot should connect with undot. Similarly on secondary side. Clear? All of you clear this? Secondary also same as it is. Voltage ratio or voltage rating both are same. So you don't take this, take the previous only. Correct polarity you take. So you take correct polarity here. Dot is connected with dot, and undot is connected with undot. This is the correct polarity. Both sides, wherever, suppose secondary side, this is dot connected here, and B winding secondary also you should connect. This is the dot of B, no? So dot dot should be with the same conductor or same wire. Thank you, Gopal. Yes, I will tell that is also. If voltage rating is different, what happens, I will tell. So wait for some time. Why you wait? So much curious before completion itself. Mostly I face from you. So let's wait for some time. All points will come. Okay. Next, third condition. Third condition. You have seen first two. Voltage rating should be same. Polarities of two transformers should be same. Next, third one. Third. So this third point is related to three-phase transformers. Not for single phase, it is three phase, because we have phase sequence for three phase but not for single phase. No, phase sequence, the phase sequence of two transformers should be same. So I will give all the figures again, just write the points first. Write the condition. Third one, the phase sequence of two transformers, phase sequence of two three phase transformers, two three phase transformers should be same. Should be same. This is for three phase transformers only. For example, transformer A having the phase sequence A, B, or take R, Y, B. Transformer A having phase sequence R, Y, B. So I will draw the figures, just right. And transformer B also should have same sequence R, Y, B. Then only it is possible to operate properly in parallel. Otherwise, circulating currents again will flow. So how it is, I will show you. First, take the fourth point also. Third condition is the phase sequence of two three-phase transformers should be same. Next, fourth, the phase displacement. The phase displacement between two transformers, should be zero. Should be zero. Or two transformers should have same displacement, same phase displacement. Two transformers should have same phase displacement. So what is this? I will give with figures now, these 2 points. So previously we have seen in three-phase transformers vector groups, 30-degree lag, 150, or 1 o'clock, 5 o'clock, 7 o'clock, like that. So that is we will apply here. So what is the need of that vector groups? We will see here. See that. Now let us consider transformer A here. I am drawing transformer B here. Now I will take both having same sequence and both having same displacement. Okay. Now I am taking, or first I will take different displacement directly. Transformer A is of DD0 connection, DD12 or DD0, anything, 0-degree connection. Now transformer B I am taking DY1 connection. Two different groups I taken. Now what is DD0 means? DD0 means 0-degree. So I will take from 0-degree, it is starting. R phase Three phase signal I'm drawing here. Three phases, R phase it is. R. Next, Y phase lags R phase by 120 degrees. Y phase I will take with black. This is Y phase, lags R phase by 120 degrees. Okay, this is Y phase. So completing this. This is Y. Next, B phase again lags Y phase by 120 degrees. This is my B phase. If you complete this, like this we get. This is B phase. So draw simultaneously. Draw simultaneously diagrams. So transformer A is a DD0 connection. Sequence is RYB. Okay. Now transformer B also having same sequence, but DY1 connection I taken. Now see what happens here. DY1 means let this is 0 degree. This is DY1 means what? 30-degree lagging connection. So it will start its R phase after 30 degrees, from 30 degrees. This is R phase, R phase it is. Next, Y phase from the here 120 degrees, Y phase. Next, B phase again 120 degrees from Y phase. Okay, like this. This is B phase. So after 30 degrees, R is started. R is started after 30 degrees. Now observe, check at any instant. At any instant for R phase, Y phase, B phase, the voltage difference must be zero in every phase. Then only circulating current is zero. But check, is it zero or not? Suppose I'm taking with respect to this first figure, this is 90 degrees now. Here 90 degrees it is, 0, 90 it is. Now at this 90-degree instant, draw a line. At this 90-degree instant, what is the voltage of transformer A R phase? Maximum. In transformer B, what is the R phase voltage? Is it maximum? No, little less. Means some voltage difference you are getting or not? Yes. So there is a circulating current in R phase. Small circulating current, small voltage difference, small current. Like that, in Y phase also you take. Y phase also, anywhere you take. Suppose this is the Y phase voltage here, and here Y phase voltage is this much. This is a small voltage, this much, but this is a large voltage in Y phase. So there is some voltage difference again in Y phase of both transformers. So circulating current in Y phase. Similarly, circulating current in B phase. So is it the best parallel operation? No. Best means this current should be zero. When current is zero, suppose if you take B, transformer B also DD0 connection, or let us take YY0 connection, anything, then R will start from zero only. Then exactly both transformer A and transformer B, RYB are in phase. Then circulating current is zero. So one condition is phase sequence. If it is RYB, it should also be RYB. Then only circulating current zero. Fourth condition is what? Displacement. If transformer A having 0 degree, transformer B also should have 0 degree only. Otherwise, circulating currents again possible. So for that reason, you should have same displacement for two transformers. Okay. If transformer A is some YD1, transformer A YD1, then what should be the transformer B also? Should be 1 o'clock connection. Maybe anything that is. Suppose DY1 is there, you can operate. Both should have same displacement, or difference between the displacement should be zero. If it is 30-degree lag, this is also 30-degree lag. Now what is the difference in these two? Zero. Displacement should be same, or the difference in the displacement, if you take, it should be zero. Clear all of this? Take the figures quickly. So below that figures, you can take 1 point if you want. Below the figures, take 1 point. Right. Due to different displacements, due to different displacements, due to different displacement, there is a possibility of, there is a possibility of circulating currents. There is a possibility of circulating currents. There is a possibility of circulating currents due to difference in voltages, due to difference in voltages in all the three phases, due to difference in voltages in all the three phases. Hence, the displacement of two transformers should be same. The displacement of two transformers should be same. Make a note. Make a note below that. Note. To operate two transformers in parallel, to operate two transformers in parallel, to operate two transformers in parallel, the two transformers, the two transformers should be belongs to, should be belongs to the same phasor group, should be belongs to same phasor group. The two transformers should be belongs to same phasor group. Same phasor group. So yesterday we have seen about phasor group. Two groups we have. Group 1, group 2. Now I will give one question, try to answer. Try to answer this. See. A transformer YD11 is suitable to operate in parallel, is suitable to operate in parallel with dash, is suitable to operate in parallel with dash. Options: DD0, YY6, DZ11, YD, DY7. What is the answer? So there is a transformer YD11. Now you need to take one more transformer which is suitable to operate in parallel. Tell what is the answer? What is the answer? Yes, whatever I expected, same. Okay, enough. Wait. Most of you given answer is C, but this is wrong. Answer is D for this. Answer is D. So wantedly I given this. Actually, these two are one group. These three are one group. Phasor group 1, that is. In group 1, do you get 11 o'clock first? No. So wantedly I given 11 here. Actually, DZ11 we don't have. These three belongs to phasor group 1. Which connections are possible here? 0 degree, 180 degree. Only these two possible. 11 o'clock is not there first in that. So answer is, this is no. So don't look at 11. Concentrate the adjacent also little. Answer is D. But now you will get doubt. How 7 we can operate with 11? We cannot operate directly. But there is a YD11. Okay. If you take DY7, can you operate directly in parallel? No, you cannot operate. What is the difference? Both are not having same. It should be same. Then only we can operate. So for that, what you need to do is you can change. See, 7 you can change to 11. A delta star you can connect in 4 ways: 1, 5, 7, 11. If it is 7, let us change the connections little bit inside, and then it convert to 11. Now you can operate these two in parallel. Okay, like that. The two transformers should belongs to same group. You have to observe that point. Same group is given or not. Suppose group is same, so I will give some other options like this. See, they given like this: DD6, YD7, DY11, YY0. Now what is the answer? Now what is the answer? Yes, what is the answer now? Yes, good. Yes, right. The answer for this is C. Because YD7 also you can operate, but directly 11 available, then why should we go with 7? Because if you choose 7, again you need to change 7 to 11 here. That is again difficult task. So for that reason, based on the options given, we have to choose. Answer is C for this. Directly 11, YD11, DY11 you can operate directly. Okay. So we have seen necessary conditions. Let's see now desirable conditions. Desirable conditions. Setting desirable conditions. Desirable conditions. Desirable means these conditions are not necessary, just desirable. Maybe in some job notifications also they will release desirable qualification, necessary qualification. Desirable means not important. Necessary is the important for us. Desirable means if it is also satisfied, still better. If not satisfied, okay, we can operate in parallel, no problem. Now here the first condition is right. The voltage rating of two transformers. The voltage ratings of two transformers should be same. Of two transformers should be same. Yes, now you people may get doubt. Previously this condition already we taken. Again, why we are taking this? This is necessary condition, no? First condition there we written. Again, I am taking the same condition here because voltage rating is both necessary condition and also desirable condition. What is desirable? If voltages are not same, then also we can operate. But how much and why it is necessary previously? Yes, it is both. So I will tell difference here. Object. Previously I taken A is transformer A 400 by 200 volt. Transformer B 400 volts by 200 volts. Okay. Actually both should have 100% same voltage, but practically it won't possible. If you design any number of transformer from same company also, little variations in voltages will come, but they will give 400 by 200 for all transformer data. But if you exactly measure, some differences will come. Like desirable means, now I will take this is 390, this is 200, and here some 401, this is some 199. Can we operate these two in parallel now? These two? Yes, you can operate. Slight difference in voltage. See, primary side 390, 401. What is the difference? 11 volts, the primary side. Secondary side, how much difference? 200, 199. 1 volt difference. So due to 11 volt, there is a circulating current on primary. Due to 1 volt, there is a circulating current on secondary also. But how much current that is? Small current. Previously, I said polarity 800 volts is voltage we are getting. That is very high current. But how much voltage here? Very, very small. So due to that, there is a small circulating current. But we can operate in parallel or not? Yes, you can operate. But can you operate like this? First one 400 by 200 and second one 300 by 200. Can we operate these two in parallel? No. Why? How much difference? Primary is 100 volts difference. You should not operate in parallel. If there is very high voltage difference, you should not operate. So this is a necessary condition. Necessary and desirable. Slight variation accepted, but not so much variation. Clear all of this? This condition is both necessary and desirable condition. Slight voltage difference, still we can operate. Next, second condition. Second, this is interesting. Listen, second condition is interesting. Suppose there are two transformers. One is 10 kVA transformer, other is 20 kVA transformer. Okay, two transformers are there, same voltage rating, kVA rating, no need to same. So you can observe in your streets also, and one transformer will be big size, one transformer will be small size. They are different capacities, but voltages are same. Same voltages, but different capacities. Yes, kVA rating, no need of same. Now let us consider transformer A 10 kVA, transformer B 20 kVA. Both connected in parallel, supplying some load. Now tell me, which transformer should supply more? 10 kVA or 20 kVA? That is general common sense, no? Whatever transformer is having higher rating, that should supply more. And whatever less rating, that should supply less. Then how it is possible? You tell to the transformer. You tell to the transformer, you share more, you share less. They will share. They will listen us first. They will listen. Never. Then how it is possible? Yes, for this we need one condition. If you apply this condition, no need to tell. Automatically they will share based on their capacity. That condition is impedance condition. Okay, so understanding what is this? If you satisfy this impedance condition, they will share the load based on their capacity. If capacity is higher, it will share more. As capacity is less, it will share less to the same load. Okay, so write that condition first. Write the condition. Condition. In order to share the load, in order to share the load based on their capacity, based on their capacity, the condition is the ohmic value of impedance. So I will write this condition again in example, so there you will understand still better. Write the condition first. The ohmic value of impedance, the ohmic value of impedance should be inversely proportional to should be inversely proportional to its kVA rating. Its kVA rating. Okay, should be inversely proportional to its kVA rating. Or the same condition in other way also we can write. Right? Or same condition in other way. Or the per unit impedance of two transformers. The per unit impedance of two transformers should be same, should be equal based on their respective kVA rating. Based on their respective kVA rating. Per unit impedance of two transformers should be same. Suppose transformer A per unit impedance 0.5. Transformer B also should have 0.5 only. Then they will share the load based on their capacity if this condition is satisfied. So many times in competitive examinations, they given this condition. per unit impedance of two transformers should be equal based on their kVA rating. Okay, now let's see what is this condition. See, the condition is like this. Consider this is transformer A. Transformer A, this is transformer B. And both connected in parallel supplying a load. Transformer A having rating SA, kVA rating it is, and it is impedance having ZA. Transformer B rating is SB, impedance is ZB, and transformer A current is IA, transformer B current is IB. Okay, then this is the total load current, and this is terminal voltage V2. This is load. Now I take an example is what? SA equal to 10 kVA and SB equal to let 20 kVA. Two transformers, different capacities, but voltage rating same in parallel. Now, how much IA, how much IB? Which current should be more? Total current IL is the sum of two currents, IA plus IB. Okay, total current. Then which current should be greater here? Because 20 is higher, no? So IB should be higher. Then how it is possible is with this condition. What is that? Impedance should be inversely proportional to kVA rating. Ohmic value of impedance inversely proportional to kVA. So according to this, if I write ZA inversely proportional to SA, ZB inversely proportional to SB. Now observe, what is SA? Only 10. SB is 20. As SA is low kVA, what should be the impedance of transformer A? Higher value. Transformer A you should design with high impedance, and SB is high value 20. So ZB value should be less. So you should design transformer B with low impedance in that. So with low impedance you have to design. So if impedance ZA is greater, what is the current IA? The current voltage is V2 in parallel combination divided by impedance of this ZA. Similarly, IB equal to V2 by ZB. Voltage is same, but what is ZA value? High value. If ZA is high, what is IA value? Less. If ZB is small, see ZB is low value. Whenever ZB is low, your current IB will increase. So which one is sharing more current? Transformer B. So this condition, if you satisfy, automatically they will share. If high capacity transformer, high current, low capacity transformer, low current, automatically it will take place. But if condition not satisfied, what may happen? So the low rating transformer may become overload, or high rating transformer is sharing very less current. So like that, unequal, that is improper sharing may take place. But if this condition satisfied, proper sharing of load will be there based on the capacity. Clear? Now how we are getting second per unit impedance? So I will show you. This is also, I will show this is also. Now observe, from the same condition we will get this per unit condition also. See, completed this. See, what is the condition? ZA by ZB inversely proportional to capacity, SB by SA. Same condition again I written. Impedance inversely proportional to kVA rate. So that is only written. Now what is SB? How to write volt ampere in terms of volt ampere? V2 into IB or not? Voltage in parallel combination into current flowing in transformer B divided by this is V2 into IA. Okay. Now same equation I will cross multiply IA ZA. This voltage I will take a denominator V2, and here also IB cross multiply ZB divided by V2. Now what is IZ by voltage? IZ is what? Voltage drop divided by voltage. What is the term we call? per unit impedance of transformer. Therefore, this is per unit impedance of transformer A. Similarly, what is this? Per unit impedance of transformer B. So both should be same. Then they will share the load based on their capacity. Okay. So listen carefully. I will show some questions. You should answer. Next, last condition. So this is second condition in desirable. So next, third condition, last is this. Third condition. See, this condition is regarding power factor of transformers. So suppose there are two transformers, transformer A, transformer B, supplying some load. Now both transformer should operate at same power factor. If they operate at same power factor, the load sharing will be maximum. Suppose there is a load, there is two transformers, 10 kVA, 10 kVA. How much maximum they can supply? 20. But sometimes they may share less than 20. When it is? When it is if the power factors are different. If power factor of two transformers are different, then they will share less load. Overall sharing will be reduced. Suppose, first write the statement. I will give with example. This is also. Write the statement. Right. In order to operate two transformers, in order to operate two transformers at same power factor, in order to operate two transformers at same power factor, the X by R ratio of two transformers, X by R ratio of two transformers should be same. The X by R ratio of two transformers should be same. Then what is the need to operate two transformers at same power factor? That is, I will show you with the example again. Observe now. There are two transformers with a different X by R ratio. Different. If X by R ratio is different, what is the power factor angle of transformers? Different, because what is the, let transformer A impedance ZA equal to RA plus JXA. Transformer B having impedance RB plus JXB. Okay. Now phi A power factor angle we can find by how? Tan inverse X by R only, no? Tan inverse XA by RA. Power factor angle of transformer A it is. Similarly, power factor angle of transformer B, tan inverse XB by RB. So what should be the X by R ratios? Same. If X by R ratio is same, you will get same power factor for both. Then advantage is, observe. Let this is my reference voltage V2. Voltage V2. If power factor angles are equal, current lags voltage by some angle. This is IA, and IB also same magnitude, both in phase. This is IB, because phi A equal to phi B taken. If angles are same, power factors also same. Then what is the total load current? IL equal to IA plus IB. Let IA is 10 ampere, IB also 10 ampere, for example. Both are same transformers, 10 kVA, 10 kVA. So example I taken 10 ampere, 10 ampere. Then what is the sum of these two? As both are in phase, direct sum, you can directly add 10 plus 10, 20 amps load current the two transformers are supplying. Now let us take different angles. Check what happened. Suppose with respect to load voltage, the two transformers operating different power factors. So here phi A equal to phi B taken. Now I will take different. Phi A is not equal to phi B. Different angles. Now draw the figure. See, this is IA. Let us consider IA it is. IAIB same 10 amperes only, but angles is different. Due to that, again, it will cause some problem. Observe. IA is 10 ampere. This is the power factor angle. And IB, different angle. Let us take. This is IB. This is also 10 amperes. Same magnitude, but angle is different. This is 5B. Now, what is this angle? 5A minus 5B. So both are not in phase. Then if you find total load current, what is the load current? Vector addition of IA plus IB. If you find this vector addition, definitely you will get less than 20 amperes. This is the load current sharing from two transformers. Clear? If the power factors are same, then the load sharing is highest, means 20 amps load sharing. If power factors operating is different, then the load sharing is reduces. Less than 20 you will get. Check if you want. You take example 5A is some 60 degree, take 5B is some 30 degree, for example. Then what is this angle? 30 degrees. Then take vector addition of these two. IA is 10 ampere, IB also 10 ampere. How to find vector addition? Vector addition. So vector sum of these two. This is our load current. If you want, you find root of IA square plus IB square plus 2IA IB cos of angle between these two, 30 degrees. Definitely less than 20 you will get. So load sharing reduced or not? Yes. So if you want highest load sharing from two transformers in parallel, what is the condition? The two transformers should operate at same power factor. For that, X by R ratio should be same for both. Then 5A equal to 5B will come. Okay. 5A equal to 5. So maximum sharing is possible. Clear all of you this point? So all of you clear? Why we need same power factor for two transformers? See, more current means you don't think only loss increases, efficiency decrease. More current means the output is more now from transformer. More current it is sharing. Suppose one transformer 10 ampere, other transformer 10 ampere. So maximum how much we are getting? First case 20 we are getting. But in second case, both currents are 10 only. But how much at the load you are getting? Less than 20 you are getting. Then is it desirable? No. You are getting less than 20. But same currents are flowing in the transformers. Efficiencies are same. No changes in efficiencies. Same current is there. Now magnitude 10, 10. Okay. Yes, 19.3. Yes, some of you given good. 19.3 you got with that small example. Means less than 20 now. Yes. If you want highest load sharing, they should operate at same power factor. Okay. So let's see some small questions on these conditions. See the question. What is the answer? If all other requirements for parallel operation of transformer are fulfilled, which one of the following pair of three-phase transformers with given vector groups can be operated in parallel? So which two we can operate in parallel? Tell me. What is the answer? Which two we can operate in parallel? Yes, all of you right. Good. The answer is B. YD1, DY1, because these two belongs to phasor group 2. But here in first one, YD, YY, different groups. DD, DY, different groups. DD, DY, different groups. The two transformers should be same group. Remember that point, easily you can answer. Next question. Next question. What is the answer? For the parallel operation of transformers, which of the following conditions must be satisfied? What is answer? Yes. So I already said voltage rating also, voltage ratio should be same. This is also correct. And here must be connected in proper polarities. Okay. R by X ratio should be same. This is also correct. But which is the most important condition? Polarity. Whenever you see polarity in any option, that is only the first preference. Okay. Yes, right. Next question. Okay, this question we need next question I'm going because we need to complete that equations for this. This is also answer this question. If the percentage impedances of two transformers working in parallel are different, percentage impedance means what? Per unit impedance of two transformers are different. Suppose transformer A per unit impedance and transformer B per unit impedance not equal, different. Then what happened? Why we are using this condition? Suppose if both equal means what is the condition? Which condition it is? In order to share the load based on their capacity, proper sharing. But they are different. So what happened? Transformers will be overheated. Power factor of both the transformers will be same. Parallel operation will not be possible. Parallel operation still possible. What is answer? Yes, there are two chances here. So what is your answer? Yes, right. Very good. Most of you given D. This is right. And some of you may also get this one. Transformers will be overheated. But observe, when there are two transformers having different per unit impedance, means condition not satisfied. As it is not satisfied, what happened? One will be overloaded, one will be underloaded. Both will not be overloaded. Remember this. But they given transformers means both will be overheated. Only one transformer will overheat, other will be underloaded. No, that's why this is wrong. If they given one of the transformer will be overheated, that is right. That will be right. Both will not overheat. Any one only overheat. Okay. Yes, good. Next question. Try to answer this. Answer this question. Consider the following statements regarding parallel operation of three-phase transformers. It is. Take care of this. The secondaries of all transformers must have same phase sequence. Second statement. The phase displacement between primary and secondary line voltages must be same for all transformers which are to be operated in parallel. So this is right only now. Phase displacement between primary and secondary line voltage must be same for all transformers. Means same vector group should be there. So this is right. Next, the primaries of all transformers must have same magnitude of line voltages. Now, out of these two, you need to decide 1, 3. Which one is right or both are right? Primaries of all transformer must have same magnitude of line voltage. See, voltage rating should be same. So they are giving here primaries of all transformers. Primaries only they are saying, but not saying about secondary. So voltage rating of transformer means suppose 11 kV by 33 kV is there. One transformer. Other transformer 11 kV by 66 kV is there. Can you operate these two in parallel? They given primaries of all transformers. Suppose two transformers example. Primaries of two transformers should have same magnitude of line voltage. They are same, but secondary is not same. How can you operate in parallel? So this statement is wrong. They should give here the line voltages of both the primary and secondary should be same, not only primary. So this is wrong. And what about first? Secondaries of all transformers must have same phase sequence. So we need a phase sequence should be same. That is our condition. But they given only secondary. And what about primary? That means primary should have same sequence or not? Yes, they also should have, but here there is one logic. They given only secondaries. This is correct because why it is correct is secondary phase sequence completely depends on primary sequence. If primary given RYB, you will get secondary also RYB only. If primary given RBY, you will get secondary also RBY only. So sequence, phase sequence on secondary completely depends on primary set. So there no need to tell now primary also should have same sequence. Secondary is having same sequence means automatically primary is also having same sequence. So one also correct means two statements is right, or 1 and 2. Option C is correct. Okay. See, regarding phase sequence, clearly you will get in alternators. Phase sequence here we can say only either RYB sequence or RBY sequence. Sequence is this sequence of voltages. Clearly about this you will get in alternators. Okay, so with this I will stop here today, and tomorrow we have only one numerical model in parallel operation. Just 15 minutes we complete. After that we start auto transformers. So by tomorrow we complete transformers. Same 5 to 9 will be there, evening 5 to 9 p.m. Okay. So today I may not attend all of you, maybe one or two only I will take for doubt session. Okay, because I have some other session after this. Yes, sir. Jitendra.
Hello.
Tell me, Jitendra.
Good evening, sir. Sir,
Good evening.
in the third point, in the desirable conditions, you told
Hmm.
that
Hmm.
X by R ratio of two transformers should be same. Sir, but
Yes.
the power factor is depending on load, no? So how you are saying the power factor phi
Uh,
A is
because transformer X by R both we are considering no for both same we are comparing anyhow. So load power factor whatever is there it will affect both the transformers. So we can neglect that small effect. Suppose load is UPF no,
yes, sir.
where transformers will operate nearly that UPF only they will operate. Okay, so remember load operation. If load is UPF, what is the primary of transformer operating?
UPF.
Nearly means little lagging will be there, but lagging it is. And if you take other transformer also, it will also lagging. No, same power factor. No, both.
Yes, sir.
Yes. For that reason, I taken directly X by R ratios of two transformers.
Okay. And sir, you said that when like transformers that are there in our locality, they are
Hmm.
like three phase transformer completely.
Hmm. Hmm.
So sir, how they are operating, like one single phase is gone sometimes and other phases.
No problem because they may become unbalanced if all phases is not having proper load or not supply. That is unbalanced. Due to that only sometime in our home you can observe low voltages we have.
Okay, and some phases
Hmm.
high voltage.
Yes. Yes. Due to
Okay, sir.
unbalanced.
So, but three phase transformer only they are using directly.
Yes, yes, yes. Three phase means from the secondary star is there now. From star only we are getting supply. Single phase to neutral.
Yes, sir. Okay, that's all, sir. Thank you.
Okay, okay. Hello.
Hello, sir. Good evening. Sir,
Tell me.
in doubling effect, in order to protect the winding, we are giving insulation only at the end.
Yes,
Can you
yes.
tell it? Can you explain it once again? Why only winding? I mean, insulation is given at the end.
Simple, simple. This doubling effect is transient effect, no?
Yes, sir.
Means for very fraction of second only it will be there. Now
Yes.
that effect mainly takes place from the source to the nearest winding turn. Suppose positive half cycle is coming. Positive half means current is from upward direction. Let us consider. Then which
Yes.
part is affected? That positive topmost.
Yes, sir.
If it is negative half, current will flow from bottom,
Yes, sir.
and
Got it,
that
sir.
bottommost will affect for that reason.
Understood, sir. And in desirable condition, like
Ah,
we have told that
ah,
per unit impedance of two transformers should be equal. Like while
ah,
explaining question in 89F, like
ah.
they that condition need to be satisfied or else need not to be satisfied.
No, if that condition satisfied, that is advantage for us. If that condition also not satisfied, you can operate in parallel. But what happened? They will share load. One will share overload. One will share underload, less load. Proper load sharing will not take place.
Thank you, sir.
Sir, good evening, sir.
Tell Anil Kumar.
Sir, in 55F, sir.
50.
Five.
Tell me.
This, can you please explain the second point, sir? KVA of open delta equal to.
Okay, listen. KVA of open delta, actually, how much we got? Only root 3 V2 I2 we got.
Yes, sir.
Okay, but here KVA delta delta how much? 3 V2 I2.
3 V2
Suppose a delta delta transformer supplying its full load.
Yes, sir.
Full load means 3 V2 I2 only, no load.
Yes, sir.
Same volt ampere rating. Suddenly in delta one phase is fault, then it is immediately open delta.
Yes, sir.
But load is there, same load 3 V2 I2. Load is same connected.
No,
So
sir.
load capacity 3 V2 I2 means this open delta has to supply same 3 V2 I2 or not,
Yes, sir.
because load will take whatever load capacity is there.
Yes, sir.
So in order to make it is, in order to bring 3 V2 I2, how can we change it is root 3 V2 and current we should increase by root 3. Then only it will become 3 V2 I2.
Okay, sir.
Okay.
Okay.
So I2 3 V2 I2. So here root 3 I2 we taken. Root 3 times of I2 means current rating will increase beyond its capacity. So we need to reduce the load by root 3 times.
Thank you, sir.
Last
Sir, good evening, sir.
tell.
Sir, in 59F, sir.
Hmm.
Sir, here directly we cannot take that as root 3 by 2 times of delta, sir.
Root 3 with 2 times of
The KVA by delta bank.
actually KVA, this is 3 V2 I2 they given, for example 30.
Okay.
Now root 3 V2 I2 required. KVA open delta how much? Root 3 V2 I2 only now.
Yes, sir.
Then how can we find this root 3 V2 I2? Directly we have the relation now, open delta capacity and delta delta.
Okay, sir.
Directly use this 1 by root 3 times of delta delta.
Okay, sir. Sir, then in 74F, sir.
Hmm. Okay.
Sir, here you said it is second wave is dominant, no, sir? How it is, sir?
Because IMU here magnetic induced current is unsymmetrical current, no? Positive values is more, positive is more because flux is positive, not there 2 phi m.
Yes,
That's
sir.
why this is also in positive half cycles will come, and after a small time steady state will come. So during that it is unsymmetrical curve. So any unsymmetrical curve will have the harmonics of both
Even.
odd and even. So after fundamental, what is that? Second. That's why it is dominant.
Okay, sir. Sir, in 71F, sir,
Hmm.
that graph also you have drawn, sir.
Mm.
Sir, in that, how we are drawing for t equal to 0 and t equal to 0 plus, sir, like the overlap.
Suppose at t equal to 0, I closed the switch where voltage is 0 here.
Okay,
Now
sir.
at that voltage 0 point, according to this relation, how much flux should be there in the core? Maximum steady state flux.
Yes, sir.
But not possible, no. So the actual producing flux is started from 0 like this, and it is becoming double the maximum.
Okay, sir.
That is doubling effect.
Okay, sir. And it will be in positives only now, sir.
Yes, positive only.
It won't get negative, sir, because it is
This
in
is
phase with current, no, sir.
transient. It will deviate. It won't be in phase with current now. It is deviated. But
Okay, sir.
after a small duration, after transient period is expired, then it comes to actual in phase with current.
Okay, sir.
So today I will close. Tomorrow we see, because there is no time again. So tomorrow 5 to 9. Good night.